Hello there and welcome to Physics with William, where big ideas are handled slowly, carefully and with enough calm to let the mind settle while the universe does its strange and often inconvenient work in the background. Tonight we're going to spend some time with a question that sounds simple when said aloud and deeply unreasonable the moment you stop to think about it. Can two things affect each other instantly? Not quickly, not almost at once, not so fast that the delay is too small to notice. Instantly, as in no travel time, no waiting, no signal crossing the gap. One thing here, another thing there, and somehow what happens to one appears tied to the other at once. It is the sort of question that seems as though it belongs in a late-night conversation between friends who should probably have gone to bed an hour earlier. It has the same flavour as asking whether the universe keeps secrets on purpose, or whether reality is better behaved when no one looks directly at it. And yet this particular question is not just a playful curiosity, it sits very close to the centre of modern physics. It touches quantum mechanics, the limits of cause and effect, the speed of light, and our basic assumptions about what it means for two events to be connected at all. It led to one of the most important insights of the 20th century, an insight known as Bell's theorem, named after the physicist John Bell, who had the audacity to turn a philosophical discomfort into a precise scientific test. Before we get there though, I would like to begin where these quiet night journeys often begin, with you. Where are you listening from tonight? Is it late where you are, with the room dim and the day finally loosening its grip? Or is it early, the kind of hour when the world still feels undecided and the light has not quite settled on what sort of morning it wants to be? Perhaps you're in a city where the sound of traffic never fully stops, or in a small town where the silence is broken only by a train in the distance, or by a dog several houses away arguing with a mystery no one else can detect. And while we're asking fitting questions, what time is it for you right now? There is something pleasing about that, I think. A discussion about how things can be connected across distance, while people scattered all over the world are listening from their own little patch of evening or morning, each arriving at the same thought from a different corner of the clock. If you find this kind of slow scientific wandering soothing, or useful, or simply a pleasant way to let the day fade out of focus, a like and a subscription would be warmly appreciated. It helps this quiet corner reach other people who may also want an hour of gentle confusion in the company of physics. And if by some chance the subject keeps you awake rather than lulls you towards sleep, then at least you will have spent that extra wakefulness in excellent company, with photons, philosophers, and a few deeply stubborn physicists who refuse to let a strange question rest. Now, it is worth saying from the outset that the question can two things affect each other instantly is not really about ordinary objects in the everyday sense. It is not about whether one billiard ball can hit another without crossing the table, or whether your toaster can sense your breakfast intentions from another room and begin working out of loyalty. Physics, frustratingly, offers no support for psychic kitchen appliances. The issue arises in a much stranger setting, a world of tiny particles and measurements and probabilities, where familiar intuitions begin to fail us in ways that are not just inconvenient but fundamental. And one of the reasons this topic is so famous is that it seemed, at least for a long time, to challenge one of the strongest habits of physical thinking, the habit of believing that influences spread locally through space. That idea of locality sounds technical, but at heart it is very straightforward. If something here affects something over there, then the effect should not leap across the gap without a mechanism. There should be some chain, some signal, some transfer, some process unfolding through the space in between. The world, as we usually imagine it, works by neighbourhoods. Nearby things interact directly. Distant things interact by passing something along. If you switch on a lamp, the room does not become bright on the far wall before it becomes bright near the bulb. If thunder rattles your windows, the sound does not reach the back garden before it crosses the front yard. Causes spread. They do not simply appear wherever they please. This way of thinking became even more disciplined after Einstein. One of the great lessons of relativity is that there is a strict speed limit built into nature. Nothing that carries usable influence can outrun light in empty space. That principle is not just a suggestion, not just a rough guide for well-behaved particles, it is woven into the structure of modern physics. So if anyone comes along and says that something can affect something else instantly across a distance, alarm bells should ring immediately. Either the claim is wrong, or it means something subtler than it first appears to mean, or else reality is stranger than many physicists were prepared to accept. And that brings us toward the real source of trouble, quantum mechanics. Quantum theory is one of the most successful scientific frameworks ever created. It predicts the behavior of atoms, electrons, light and matter with astonishing accuracy. It sits behind the technologies that shape modern life, from lasers to semiconductors to magnetic imaging. It is tested constantly and it keeps passing those tests with unnerving confidence. But from its earliest days, even many of the people who helped build it were uneasy about what it seemed to say. The mathematics worked beautifully. The picture of reality hiding behind that mathematics was much harder to love. One particularly troubling feature was the idea that particles could become entangled. That word will matter a great deal as we continue, so it is worth sitting with it for a moment without rushing. Entanglement means that two particles can be prepared in such a way that they no longer have entirely separate descriptions. You cannot fully describe one without also referring to the other, even if they later move very far apart. Their properties become linked in a way that is stronger than ordinary correlation. Not like two socks from the same pair, where one being striped tells you something about the other because both were made together. This is deeper and stranger. In quantum mechanics, the connection seems to persist even when the particles are separated by a large distance, and when a measurement is made on one, the outcome for the other is tied to it. That does not sound too disturbing at first if said casually enough. After all, there are many ordinary cases where learning something about one thing tells you something about another. If I put a red card in one envelope and a blue card in another, shuffle them, and mail one envelope to Amsterdam and the other to Buenos Aires, then opening one instantly tells you what is in the other. No mystery there. The cards had definite colours all along. The information was merely hidden until the envelopes were opened. The world did not perform any strange acrobatics at the moment of discovery. A natural hope was that quantum mechanics might work like that too. Perhaps these particles really do carry definite hidden properties from the moment they separate, and measurement simply reveals what was already there. That would preserve a comforting picture of the world. It would mean reality remains local and sensible underneath the strange surface language of the theory. The particles would not be affecting each other instantly. They would simply have been coordinated in advance, like two careful actors following the same script in different cities. Einstein, among others, preferred something along those lines. He was not convinced that nature should abandon locality and definite reality just because quantum mechanics was being dramatic again. But the trouble with quantum mechanics is that it rarely stops at merely being dramatic. It has a way of following its own logic into places that sound almost rude. If you take the theory seriously, it seems to predict correlations between distant particles that are stronger than any local hidden script should allow. And for years this was a matter of debate because it sounded almost philosophical. People could argue about interpretation. They could disagree about what the formalism meant. They could make stern faces and write letters to one another. What John Bell did, and this is why his name matters so much, was to show that the disagreement could be made experimental. He asked in effect, what if we stop arguing in general terms and instead ask what patterns of results are possible if the world is both local and governed by hidden properties? Then compare that with what quantum mechanics predicts. If the two sets of predictions differ, nature can decide. That step was extraordinary because it converted a murky dispute about the meaning of theory into a clean challenge that laboratories could eventually answer. Bell showed that if local hidden variables are the true story, then the correlations observed between distant measurements must stay within certain limits. Quantum mechanics predicts that in some situations those limits will be exceeded, not by a little interpretive flourish, but by measurable amounts. So now the universe had a choice to make. It could preserve locality in the strong classical sense, or it could preserve the quantum predictions that had already earned considerable trust, but apparently not both together in the way many people had hoped. And this is where the opening question begins to sharpen. When two entangled particles are measured far apart and the results come out correlated more strongly than any local hidden account permits, what should we say has happened? Has one thing affected the other instantly? Has some kind of information outrun light? Has locality itself failed? Or are we using the wrong language altogether, trying to force an unfamiliar quantum situation into classical ideas that simply do not fit? Physicists have been discussing those questions for decades, and while there are answers of a sort, they are not the kind that tuck themselves neatly under the pillow and behave. Still, it helps to keep the problem grounded. One reason this subject can feel slippery is that the words we use are ordinary while the behaviour they point to is not. Affect, instantly, distance, cause, information. Each of these terms carries habits from everyday life. We think of influence as a push or a pull. We think of instant as zero waiting time on a clock. We think of distance as a stretch of space that must be crossed. Quantum physics does not always reject those habits outright, but it often rearranges them until they no longer sit where we left them. That is why discussions of Bell and entanglement can feel as though the floor remains stable, while the furniture quietly moves itself around the room. It is also why this topic drew such intense emotional responses from physicists themselves. Einstein famously disliked the idea that the quantum description could be complete if it allowed these puzzling distant correlations. He wanted a deeper theory underneath, one in which physical properties existed independently of observation, and no influence slipped mysteriously across space. Niels Bohr, by contrast, defended the quantum framework and argued that Einstein was demanding from reality a kind of picture it was under no obligation to provide. Their debates were not mere academic sparring. They reflected a genuine clash about what science should aim to describe. Should a theory tell us what is really there, independent of measurement, or is it enough for it to tell us what outcomes we should expect when experiments are performed? That tension runs through the whole story like a quiet current, and perhaps that is part of why Bell's theorem remains so compelling. It does not merely solve a narrow technical problem. It tells us that some of our cherished intuitions cannot all survive together. If we insist that physical properties are definite before measurement and that influences remain local, then the world should obey certain statistical rules. Quantum experiments do not. Something has to give. Either locality or a straightforward form of realism, or some assumption about independence and measurement choice, or perhaps our way of carving the whole problem into categories. Different interpretations of quantum theory sacrifice different comforts, rather like choosing which piece of furniture you're willing to lose when moving into a smaller apartment. Everyone has preferences. No one gets everything. For tonight, though, I do not want to rush ahead to the final philosophical bookkeeping. It is better to let the unease arrive gently and in the proper order. The central question only feels as strange as it should if we first remember what kind of universe physicists thought they were living in. A universe where causes propagate continuously. A universe where distant objects do not coordinate themselves in impossible ways. A universe where if two things line up suspiciously well, one assumes either a common cause in the past or a signal sent through the ordinary channels of space and time. Bell did not begin by inventing weirdness. He began by asking whether that familiar picture could be saved beneath the quantum surface. The answer, as experiments would later suggest with alarming consistency, was no. That no did not mean we can send messages faster than light whenever we like. This is an important point, and one that often gets muddled in popular retellings. Entanglement does not let you phone Mars instantly, or win at causality by quantum trickery. The correlations are real, but they do not function like ordinary controllable signals. You cannot choose the result on one side and thereby force a chosen message onto the other. Nature very irritatingly keeps the strangeness while denying us the useful shortcut. It is as though the universe agreed to be deeply non-classical, but refused to become convenient. even so, the implications remain remarkable. The fact that two distant systems can display linked outcomes beyond what local hidden explanations allow means that the world is not stitched together in quite the way classical common sense imagined. There are relations in nature that cannot be understood merely as local pieces carrying pre-assigned instructions from a shared past. Something about the structure of reality is more holistic, more interdependent, or at the very least less classically separable than Einstein would have liked. Whether that counts as instant influence depends on the interpretation, and physicists can still spend a perfectly respectable amount of time disagreeing about the wording. But the old dream of preserving all the familiar intuitions at once has not fared well. So as we settle into this story, the useful thing is not to demand an immediate answer, but to keep the tension alive. On one side stands locality, the deeply persuasive idea that what happens here should not be changed at once by a choice made far away. On another stands realism, the belief that physical properties exist in a definite state whether or not anyone checks them. On a third stands the formidable success of quantum mechanics, which keeps predicting outcomes that experiments stubbornly confirm. Bell found a way to show that these commitments do not all fit together, and once that door opened, physics had to walk through it whether it liked the decor or not. In a way, this entire discussion begins with a very human discomfort. We do not mind mystery in moderation. We can tolerate not knowing exactly what dark matter is, or whether the universe curves back on itself somewhere beyond our reach. But we do like the nearby world to keep its manners. We prefer causes to remain attached to effects by visible thread, or at least by thread of the sort a good theory can point to without blushing. Bell forced physics to face the possibility that the thread is there in a form unlike what classical reasoning expected, and that our picture of separate things in separate places may be less complete than it appears in daylight. And that is where the path ahead leads naturally. Before Bell could show what local hidden theories cannot do, there first had to be a growing unease about quantum mechanics itself. There had to be particles behaving in ways that seemed statistically ordinary on the surface and conceptually intolerable underneath. There had to be Einstein raising objections, not because he disliked novelty, but because he thought a physical theory should not ask us to abandon locality and definite reality without an excellent reason. The next step, then, is to move closer to that discomfort, to see why distance was expected to keep things apart, and why quantum mechanics began to suggest that keeping things apart was not going to be nearly so straightforward. There is a reason the idea of instant connection feels so unsettling, and it is not just because quantum mechanics enjoys behaving like the one dinner guest who smiles pleasantly while overturning the furniture. It is unsettling because distance, in almost every ordinary experience we have, seems to mean something real. It is not just a gap on a map. It is a kind of protection, a buffer, a rule that says what happens here stays here until something has had time to travel there. Distance gives the world order. It gives causes a route to follow. It gives events a sequence. Without it, reality starts to feel less like a place and more like a rumour. Think for a moment about how thoroughly this expectation shapes your daily life. If someone drops a glass in the kitchen, the sound does not reach the far end of the house before it fills the room around the break. If lightning flashes over a field, the light arrives first and the thunder follows later, not because the storm is being dramatic for its own amusement, but because signals take time. If a friend sends you a text from another city, the message does not simply appear because two phones share a sentimental bond. Something has to carry it. There is always some process in between. Even in the age of wireless communication and invisible signals moving through the air, we still rely on the same principle. Effects do not just show up at a distance without a story connecting them. This may seem so obvious that it hardly deserves saying, but in physics, the obvious things often do the most important work. They become the quiet assumptions beneath everything else. Long before anyone worried about entanglement or Bell, or the unnerving behaviour of photons, scientists built their picture of the world on the belief that space matters. If two things are far apart, then whatever joins them must somehow bridge that separation. You might not always see the bridge. It might be a field or a wave or a moving particle or a chain of local interactions. But there should be one. Nature, on this view, is a local business. Each patch of the world deals directly only with its nearby patch, and distant coordination happens through influences that travel step by step. This local picture is not just tidy, it is also deeply successful. You can see it in mechanics, where pushes and pulls transmit motion through contact or through forces that are described across space. You can see it in waves, where disturbances move through water, air or fields in a continuous way. You can see it in engineering, in astronomy, in every attempt to predict what happens next by knowing what is happening now in nearby places. It is one of the reasons physics became so powerful. The universe seemed to be built from parts arranged in space, each affecting the next according to clear rules. The world could be understood by studying how local pieces fit together, and then, as often happens, light arrived to complicate everyone's confidence. By the 19th century, physicists had come to understand light not as a stream of mystical brightness or a decorative blessing for landscapes, but as an electromagnetic wave. James Clerk Maxwell brought electricity, magnetism and light into one grand theoretical framework, and the result was magnificent. The equations predicted that electromagnetic disturbances should travel through empty space at a fixed speed, and that speed turned out to be the speed of light. This was one of the great triumphs of physics, but it also planted a problem. A fixed speed for light meant that ordinary ideas about motion and timing were not going to survive unchanged. Einstein took that problem seriously, and what he gave us in return was relativity. One of the most important consequences of relativity is that the speed of light is not just a property of light. It is a limit built into the structure of the universe. No usable influence, no ordinary signal, no object carrying information can outrun it. This matters enormously for our story, because it turns locality from a general common sense principle into something sharper. It is no longer just that distant things should not affect each other without a bridge. The bridge itself is constrained. It cannot carry its influence arbitrarily fast. Space and time together impose discipline. That discipline has a profound consequence. If two events are separated by enough distance and happen close enough together in time, then there may simply be no way for one to have caused the other through any signal that respects the speed limit of light. They must then be independent, or else share some cause in their past. This idea becomes almost instinctive once you live with relativity for a while. When physicists look at distant events, they ask not only whether one could influence the other, but whether there is enough time for any influence to get there at all. Causality becomes geometric. The universe lays out which events can be connected and which cannot, and that is why the quantum story becomes so uncomfortable. Because once you take relativity seriously, the thought that a measurement here could somehow be tied to an outcome there with no signal crossing the gap begins to sound not merely odd, but forbidden. Einstein in particular felt this acutely. For him, locality was not some optional aesthetic preference. It was part of what made physical explanation respectable. A theory should not ask us to believe that a choice made in one laboratory can somehow reshape reality in another distant laboratory at once. That would mean the world is not partitioned in the sensible way it appears to be. It would mean space does not protect independence after all. Now, one could imagine two broad ways that distant things end up correlated without violating this principle. The first is direct communication. One thing influences the other by sending something across the distance. That works well in ordinary life and in classical physics, provided the signal respects the speed limit. The second is common cause. Two distant outcomes might line up because they were coordinated earlier before they separated. Two clocks can strike together not because one secretly whispers to the other across town, but because they were both set from the same reference. Two cards placed in separate envelopes can match a pattern because someone arranged them beforehand. In such cases, the correlation is not mysterious. The present agreement comes from a shared past. That second possibility was extremely attractive to physicists who hoped quantum mechanics could be made less strange. If two particles are found to have correlated properties at a distance, perhaps that is not because anything instant is happening when they are measured. Perhaps they simply carried matching instructions all along. The measurements merely reveal the script. It would be as though the universe had packed a little note inside each particle before sending them apart, a note saying, if you are asked this question, answer this way, and if your partner is asked that question, answer that way. No superluminal mischief, no violation of locality, just hidden organisation beneath the surface. At first glance this sounds entirely reasonable, and in a different universe it might even have been correct. The problem is that quantum mechanics does not behave like a theory of sealed instruction packets. The correlations it predicts are too strong, too delicately structured, too dependent on how measurements are chosen. A classical hidden script can explain some agreement, but not the full quantum pattern. That is the result Bell would later make precise. Before Bell, though, the discomfort was already present in embryo, because even the standard quantum formalism seemed to treat distant systems in a way Einstein found intolerable. To see why distance was supposed to keep things apart, it helps to think about what separation means in ordinary physical reasoning. When two objects move away from one another, we imagine them becoming more independent. Each goes on to have its own local environment, its own interactions, its own story. If I take a pair of gloves and put one in a box on a train and one in a box on a ship, then send them in opposite directions, nothing mysterious happens when one box is opened later. The gloves do not remain in some deep state of physical togetherness. They are simply separate objects with definite properties. My discovery of one glove tells me something about the other, but only because the pair was well defined from the start. Separation does not preserve any strange unfinishedness. It reveals what was already there. Quantum mechanics resist this picture. When two particles are entangled, the theory often does not assign each particle its own neat set of independent properties. Instead, it assigns a joint state to the pair. That joint state can be perfectly clear about the relation between outcomes while leaving each individual outcome undetermined until measurement. It is as though the pair has a definite rule for how their answers will fit together, but not a definite set of pre-written answers for every possible question. This is what makes the situation so different from the glove example. With gloves, one box contains left and the other contains right, whether or not anyone looks. With entangled particles, the theory says something more slippery. The pair as a whole is specified, but the individual pieces are not specified in the classical way you would expect. Einstein was not fond of such slipperiness. He believed that physical reality should not depend on whether someone performs a measurement, especially not at a distance. If a particle is over here, far from any meddling experiment on its partner, then what is real about that particle ought to be real, regardless of what someone chooses to do elsewhere. Otherwise, the world begins to look alarmingly dependent on acts of observation, which to Einstein felt less like physics, and more like a stage play with intrusive audience participation. There is also a deeper reason separation mattered to him. Science had been built on the idea that the world can be analysed into parts. You may have a complex system, certainly, but if the pieces are far enough apart and shielded from one another, then each piece should have its own real state. That does not mean the pieces cannot have a common history. It does mean that once separated, one should not require the other in order to be fully real. Otherwise, the very notion of a physical system located here becomes compromised. A distant choice would help define what is true locally, and that is hard to reconcile with a serious respect for space-time structure. This is why the phrase spooky action at a distance became so famous. Einstein used it not as a compliment, but as a complaint. He was objecting to the idea that quantum mechanics, if taken at face value, seems to imply some kind of immediate connectedness between distant systems. He thought that was evidence the theory was incomplete. In his view, the right response to apparent non-locality was not to shrug and accept it, but to suspect that something important was missing from the theory. There had to be deeper variables, hidden facts, or a more complete description waiting to be uncovered, one that would restore locality and realism together. And one can understand why he hoped that. Once you allow distance to stop mattering in the basic structure of explanation, all sorts of old physical instincts begin to wobble, the world becomes harder to visualize, cause and effect become more delicate to define. Even the distinction between nearby and far away begins to lose some of its power. It is not that space becomes meaningless, but that separateness becomes less absolute than classical physics had promised. What had looked like a universe made of local parts starts to resemble something more intertwined. Of course, this is the part where the universe adds a small note of mockery, because although quantum mechanics undermines classical separateness, it does so in a way that remains maddeningly selective. You do not get to use entanglement like a magic rope for dragging messages across the cosmos at will. If two distant observers measure entangled particles, each sees locally random results. Only later, when they compare records through ordinary slower-than-light communication, do the striking correlations appear. So the quantum world manages to be more deeply connected than classical physics allows, while still refusing to let anyone exploit that connectedness for convenient faster-than-light messaging. It is a very particular kind of strangeness, elegant in theory and mildly irritating in practice. Still, the important point for where we are in the story is this. Distance was expected to keep things apart not because physicists lacked imagination, but because everything from ordinary causality to field theory to relativity supported that expectation. Space seemed to organize the world into regions of influence. Separation seemed to create independence unless some signal or common cause explained the coordination. When quantum mechanics suggested that distant particles might not fit into that local structure in the familiar way, it was not a minor technical quirk. It was a challenge to the underlying grammar of physical explanation. You can imagine how tempting it was to soften that challenge by saying the weirdness is only apparent. Perhaps the particles really do have definite properties all along. Perhaps the theory is incomplete. Perhaps once the hidden details are filled in, the world will become local and respectable again. Einstein, and those sympathetic to him, were not trying to cling to old ideas out of stubborn nostalgia. They were defending principles that had earned their authority through centuries of success. Distance should matter. Physical reality should be local. Distant choices should not determine local facts. These were not trivial assumptions. They were the bones of the classical worldview. Yet quantum mechanics kept producing situations that sat badly within that worldview. The more carefully one examined entangled systems, the less plausible it seemed that a simple local hidden story could account for them. If the particles carried full instructions in advance, those instructions would have to reproduce the intricate pattern of correlations predicted by the theory across different possible measurement settings. And this, as Bell would later show with wonderful clarity, is where the local hidden approach runs out of road. Nature can be local with hidden definiteness, or it can be quantum in the way experiments suggest, but it cannot be both in the straightforward classical sense. Before getting there, though, it is worth noticing something almost tender in Einstein's resistance. He was not objecting to mystery itself. He was objecting to a kind of explanation he thought lacked physical dignity. A world in which distant events are mysteriously coordinated without local mechanism felt to him unfinished. He wanted a reality that exists objectively and independently in each region of space, one that does not wait for observation to decide what is true. In that respect, his discomfort was not merely technical. It was philosophical in the best sense. He cared what sort of universe science was describing, and perhaps that is why this topic still feels alive. The question is not only whether entangled particles display stronger than classical correlations. They do. The question is what that forces us to give up. If distance no longer guarantees independence, then space is not dividing the world as cleanly as we once thought. If local properties are not all definite before measurement, then realism takes a blow. If quantum theory is somehow correct without providing the sort of local picture Einstein wanted, then explanation itself becomes less pictorial and more abstract than many people find comfortable. For now, it is enough to stay with the old expectation and feel its weight. Distance should keep things apart because that is how the world appears to be built. It should create room between events, room for delay, room for separate realities unfolding in separate places. That expectation is supported by ordinary experience, by classical physics, and by relativity. It is not childish. It is disciplined common sense, which is precisely why the next turn in the story matters so much. Because once quantum mechanics enters the conversation in earnest, that disciplined common sense begins to falter, and Einstein, who had helped teach physics how seriously to take space-time, found himself staring at a theory that seemed to disrespect it in a way he could not accept. To understand why Einstein reacted so strongly to quantum mechanics, it helps to remember something that often gets flattened in popular retellings. He was not an old man scowling at a new generation simply because the furniture had been rearranged. When quantum theory first began to take shape, Einstein was one of the people who helped make it possible. In fact, some of the earliest cracks in classical physics were widened by his own hands. He showed that light, which had long been understood as a wave, sometimes behaves in a particle-like way. He used this idea to explain the photoelectric effect, where light striking a metal can eject electrons in a manner that classical wave theory could not fully account for. It was one of the achievements for which he later received the Nobel Prize, and it placed him squarely inside the revolution from the beginning. So the story is not that Einstein failed to understand quantum mechanics. The story is that he understood it too well to feel comfortable pretending its oddities were merely temporary. He saw where the theory was pointing. He saw what it seemed to require us to give up. And unlike some of his colleagues, he never became willing to call that sacrifice harmless. His relationship with quantum mechanics was not one of ignorance, but of reluctant intimacy. The kind of relationship where you admire the brilliance, acknowledge the results, and still lie awake at night wondering whether this person is going to ruin your life. The early decades of the 20th century were a remarkable time in physics, because two great transformations were happening at once. Relativity was changing our understanding of space, time, motion, and gravity. Quantum theory was changing our understanding of matter, light, energy, and measurement. Both revolutions were profound. Both challenged common sense, but they challenged it in different ways. Relativity, for all its strangeness, had a kind of austere clarity. It told you that time is not universal, that lengths contract, that simultaneity depends on motion, that gravity is woven into geometry. These were shocking claims, certainly, but they formed a coherent picture of the world. There was elegance there, even beauty. One could imagine the structure, trace the logic, and feel that reality, though surprising, was still lawful in a deeply intelligible way. Quantum mechanics was another matter. It did not merely revise some old assumptions. It seemed to unsettle the very idea of what a physical description ought to be. Instead of giving precise trajectories and definite properties, evolving in time, it offered probabilities. Instead of describing what a system is doing independent of observation, it seemed to focus on what outcomes might appear when measurements are performed. Instead of reassuring us that particles had well-defined attributes whether or not anyone checked, it often left those attributes suspended in an unsettling not quite. The mathematics was powerful, the picture was maddening. This tension was already visible in the work of Niels Bohr, Werner Heisenberg, Max Born, and others who shaped the developing interpretation of quantum mechanics. Heisenberg introduced a new matrix-based formulation that avoided speaking too directly about hidden underlying paths. Schrödinger introduced wave mechanics, which at first looked more intuitive but soon raised its own strange questions about what exactly was waving. Born proposed that the wave function should be understood not as a physical wave in space, but as a way of assigning probabilities to possible outcomes. Bohr, with his characteristic calm and talent for making difficult ideas sound both philosophical and faintly ceremonial, argued that quantum phenomena could not be described in classical terms without essential limitations. The act of measurement was not an external convenience. It was built into the structure of what could be said. Einstein did not like where this was going. He was willing to accept that classical mechanics was incomplete. He was willing to accept that light and matter behave in ways that require radical new theory. What he resisted was the suggestion that physics should stop trying to describe an underlying reality and be satisfied with a formalism that only predicts observed results. To him, that felt like surrender dressed as sophistication. A physical theory, in his view, ought to tell us what is real, not merely what we are likely to see when we poke reality with a carefully calibrated stick. One of the central points of friction was probability. In classical physics, probabilities usually reflect ignorance. If you toss a coin and I tell you the chance of heads is 1/2, that does not mean the coin itself is metaphysically undecided. It means I do not know all the microscopic details of the toss. In principle, if I knew the exact forces, angles, air currents, and initial conditions, I could predict the outcome. The randomness is practical, not fundamental. Quantum mechanics seemed to say something much stronger. The probabilities were not just placeholders for hidden certainty. They appeared to be built into the world itself. Even with complete knowledge of the quantum state, one could often predict only probabilities for individual measurement outcomes. This was the source of one of Einstein's most famous objections, often summarized in the line that God does not play dice. The phrase is quoted so often it has become almost decorative, like a framed slogan in a physics department hallway. But the point behind it was serious. Einstein was not objecting to statistics as a useful tool. He was objecting to the idea that the deepest laws of nature might be irreducibly probabilistic. He suspected that the quantum formalism was incomplete, that beneath its successful predictions there must be additional facts, hidden elements of reality that restore determinacy. He was not insisting that the universe conform to his personal preferences out of vanity. He was defending a vision of science in which apparent randomness reflects missing description, not the final character of reality. Bohr and others saw things differently. They argued that Einstein was demanding too much from a theory and perhaps demanding the wrong kind of thing. Quantum mechanics, in their view, was not defective because it did not provide a classical picture of what happens between measurements. Rather, classical pictures were simply inadequate to the task. The quantum world could not be squeezed into the old categories without distortion. Bohr especially emphasized that measurement arrangements matter. The kind of question you ask determines what sort of answer nature can meaningfully give. Position and momentum, for instance, are not jointly available with arbitrary precision in the way classical intuition would like. The experimental context is part of the content of the result. This sounds abstract, and one can sympathize with anyone who begins to miss the simple emotional honesty of a falling apple. Einstein certainly did. He did not deny the predictive success of quantum mechanics. In fact, he used it, contributed to it, and respected the astonishing skill of those building it. But he kept probing for weaknesses, for paradoxes, for indications that the theory could not be the full story. He raised thought experiments the way some people raise difficult questions at a family dinner, politely at first, then with increasing determination as everyone else tries to change the subject. One of the most famous areas of dispute concerned the uncertainty principle. Heisenberg had shown that certain pairs of quantities cannot both be sharply specified within the quantum formalism. This was not merely a statement about clumsy instruments, it was built into the structure of the theory. Einstein tried again and again to devise scenarios that would circumvent the limitation, only to have Bohr answer each challenge with formidable patience, and a kind of intellectual judo that must have been both impressive and exhausting to witness. At conferences, especially the Solvay meetings, these exchanges became legendary. Einstein would arrive with a carefully crafted thought experiment meant to expose a contradiction or incompleteness. Bohr would spend a tense evening pacing, worrying, then return with a reply that preserved the theory. It was one of the great scientific dialogues of the century, though one suspects it did not do much for anyone's sleep schedule. What is striking is that Einstein lost many of these individual skirmishes and still did not yield the larger war. That was because his unease was not about one technical loophole here or one paradox there. It was about the overall spirit of the theory, a framework that made observation central, accepted fundamental probabilities, and seemed reluctant to describe an underlying local reality did not satisfy him. He wanted more. He wanted a theory that would explain why quantum mechanics works, while also restoring a picture of the world as made of real things with real properties existing independently in space and time. This brings us closer to the issue that matters for Bell theorem, because Einstein's strongest and most enduring objection was not just about randomness, it was about separability and locality. He believed that distant systems should have their own independent realities. If two particles move far apart, then what is real about one should not depend on what someone does to the other. That was not a narrow technical preference. It was bound up with everything relativity had taught physicists about the structure of causation. Space was not decorative. Separation was not optional. A local world should be built from local facts. And quantum mechanics seemed, increasingly, not to respect that demand. The trouble became especially sharp in situations involving correlated systems. Suppose two particles interact and then move apart. Classical intuition says each particle should carry its own definite set of properties once the interaction is over, perhaps correlated because of their shared history, but nonetheless its own. Quantum mechanics often refuses to grant that independence so neatly. It describes the pair with a joint state in which the relation between outcomes is well defined, while the individual properties remain, in a certain sense, unsettled until measured. This was not the sort of correlation one sees in a pair of gloves or two sealed cards. It was something stronger and more structurally difficult. Einstein found this intolerable because it seemed to imply one of two unpleasant options. Either the theory was incomplete, and there were hidden variables restoring definite local properties beneath the formalism, or the act of measuring one particle somehow had implications for the description of the other, no matter how distant. He preferred the first option by a wide margin. Better an incomplete theory than a world in which distant measurements participate in defining local reality. Better missing pieces than spooky influence. This is where the uneasy conversation between Einstein and quantum mechanics became especially tense. The theory kept succeeding, experiments kept supporting it. Younger physicists, or at least more interpretation-friendly ones, grew increasingly comfortable with the idea that quantum mechanics might not owe anyone a classical picture. Einstein remained unconvinced. He did not think predictive accuracy alone settled the matter. A map can get you home while still leaving out half the city. A theory can work and yet be incomplete. One must be careful here not to turn Einstein into a simple hero of realism, standing nobly against fashionable nonsense, because the history is subtler than that. Quantum mechanics was not mere fashion. It was and remains one of the most empirically successful theories ever devised. Bohr, Heisenberg, Born, and the others were not dodging reality for the fun of it. They were trying to make sense of a world that kept violating old expectations, but it is equally wrong to dismiss Einstein as simply unable to move on. His objections were deep, disciplined, and in some cases prophetic. He was asking whether the triumph of the formalism had made physicists too willing to abandon the search for an intelligible account of what exists. That question has never quite gone away. By the time the famous paper written by Einstein, Podolsky and Rosen appeared in the 1930s, the disagreement had crystallized. The paper, usually referred to by the initials of its authors, was designed to argue that quantum mechanics could not be a complete description of physical reality. The argument was subtle but devastating in spirit. If the theory allows one to predict with certainty the outcome of a measurement on one particle by measuring its distant partner, and if no disturbance can travel instantly between them, then the distant particle must already possess whatever property is being predicted. If quantum mechanics does not assign that definite property prior to measurement, then it is missing something real. That was the essence of the challenge. The response from Bohr was famously dense and, depending on whom you ask, either profoundly insightful or one of the great masterpieces of respectful obscurity. He rejected the premises of the argument, or rather the way they defined physical reality and disturbance. He insisted that the measurement context matters in a way Einstein formulation did not fully capture. Many readers have sympathized with Einstein on the grounds that if an answer requires several pages of philosophical maneuvering, one begins to suspect the question struck home. But regardless of who one finds more persuasive, the dispute marked a turning point. Einstein had made precise the feature of quantum theory he found most disturbing. Distance no longer seemed to guarantee independent reality. It is important to linger over this because it sets the emotional and intellectual stage for Bell. Einstein did not prove quantum mechanics wrong. He showed why, if taken as complete, it carries an unsettling implication. Either reality is not local in the classical sense, or the theory is incomplete. For a time, many physicists more or less sidestepped the issue. Quantum mechanics worked. Laboratories had better things to do than referee philosophical quarrels between geniuses. If the theory gave the right answers, then perhaps one could get on with using it and leave the metaphysical bookkeeping to someone else. John Bell refused to leave it there. But before Bell enters properly, one more feature of Einstein unease deserves attention because it reveals something admirable about his intellectual character. He was willing to be the dissenter in a room full of people celebrating success. That is not always a comfortable role. Science rightly values results, and quantum mechanics had them in abundance. Yet Einstein kept asking whether success had been purchased at too high a conceptual cost. He kept pressing on realism, locality, and completeness. He kept insisting that the most accurate theory available might still fail to tell the full truth about the world. There is a kind of loneliness in that position, especially when the next generation has begun treating the matter as settled. One can imagine Einstein listening to enthusiastic explanations of complementarity or measurement, nodding politely while privately thinking that everyone had become far too cheerful about abandoning common sense. He was not defending common sense in the shallow everyday sense. He knew perfectly well that physics often transcends ordinary intuition. He had done as much transcending as anyone. What he was defending was a deeper form of intelligibility, the conviction that physical reality should exist in an objective way, and that distant regions of space should not lose their independence merely because the quantum formalism finds that arrangement inconvenient. And yet the formalism kept working. That is the detail that gives the whole episode its particular ache. Einstein was not railing against failure. He was objecting to success of a certain kind, success accompanied by a picture of reality he found unacceptable. It is one thing to reject a theory because it predicts badly. It is another to reject its completeness because it predicts splendidly, while asking you to give up principles you consider foundational. That is what made his conversation with quantum mechanics so uneasy. He could not simply dismiss it. He had to live with its brilliance while refusing to grant it the last word. Eventually, this tension narrowed around a single haunting possibility. If quantum mechanics is complete, then entangled systems exhibit a kind of connectedness that cannot be understood in strictly local classical terms. If that seems unacceptable, then perhaps there are hidden variables beneath the theory, restoring both realism and locality. Einstein hoped for that deeper layer. Bell would later show that such hope comes at a price, because no local hidden variable theory can reproduce all the predictions of quantum mechanics. That realization did not arrive all at once. It emerged from the very discomfort Einstein kept alive, the refusal to treat conceptual trouble as mere background noise. So as the story moves forward, the next thing to face is the strange bond itself, the feature of quantum theory that made all of this more than a disagreement about style or philosophy. Particles could be prepared in a way that made their fates inseparable even across distance. Their outcomes were linked not like ordinary objects sharing a past, but in a way that seemed to challenge the whole idea that distant things are fully separate. Einstein saw in that bond a sign that the theory was incomplete. Others saw in it the new grammar of nature. Either way, the bond had a name, and once it entered physics for good, the old local picture of the world was never going to feel quite as secure. What made this disagreement more than a philosophical quarrel over tea and terminology was the existence of a very specific quantum phenomenon, one that refused to stay politely in the background. Einstein could argue about completeness. Bohr could argue about the limits of classical description. But underneath their exchange sat a concrete and deeply troublesome feature of the theory. Two particles could be prepared in such a way that their properties were no longer fully separate, even after the particles themselves had gone their own way. That feature came to be known as entanglement, and it is one of those scientific words that sounds almost charming, until you realise it has spent the last century quietly ruining people's certainty about how reality is stitched together. The word itself is surprisingly domestic. It brings to mind earbuds knotted in a pocket, fishing line misbehaving near a riverbank, or the sort of necklace clasp that always becomes more complex when one is already late. But quantum entanglement is not a case of particles being physically tangled together like small objects in a drawer. It is not that they are stuck or glued or linked by some invisible wire stretching through space. The bond is stranger than that. It is a relationship encoded in the quantum description of the pair as a whole. The two particles are described jointly, and that joint description contains correlations that cannot always be reduced to a story about each particle, separately carrying its own complete little set of private facts. This is where many explanations become either too vague or too eager to be dazzling, so it helps to move slowly and begin with a very ordinary kind of correlation, because entanglement only becomes truly strange when compared against familiar examples. Suppose I have a pair of socks, one blue and one green, and I place them into two sealed boxes. I hand one box to you and send the other far away. When you open your box and find the blue sock, you immediately know the distant box contains the green one. There is no mystery there. The colours were fixed all along. The boxes were separated, yes, but the contents were already determined from the start. Your act of opening one box did not cause the other sock to turn green at a distance. It merely revealed what had always been true. This kind of correlation comes from a common cause in the past, namely my original packing arrangement, and perhaps a slightly questionable sense of laundry organisation. That sort of example is often used because it sounds like entanglement at first. Two things are separated. You learn something about one and instantly know something about the other. But the resemblance is misleading. In the sock case, each box contains a definite item with a definite colour whether or not anyone looks. The information is hidden, not indeterminate. Classical reasoning loves this setup because it preserves all the comforts. The world is made of separate objects with separate properties, and distance does not interfere with that. Entanglement begins where this picture stops being enough. Imagine instead that two quantum particles are created together in a way that fixes a relation between certain measurement outcomes without fixing those outcomes individually in the familiar classical sense. If you later measure one particle and get one result, then a corresponding measurement on the other will give a linked result. But before either measurement is made, the theory does not assign the pair the way it would assign the sock boxes. It does not simply say particle 1 already has this answer written inside it, and particle 2 already has the matching answer written inside it. Rather, it gives the pair a shared state, in which the correlation is definite while the individual outcomes are not definite in the same straightforward way. That sounds slippery because it is slippery. Quantum mechanics often forces us to speak in sentences that would get a stern look from a well-trained classical physicist. The pair is well defined, but the parts are not fully well defined on their own. The relation is settled, but the individual values are not all settled in advance. The state belongs to the pair, not just to each particle considered separately. It is as if the universe keeps the answer to a duet without assigning fully independent sheet music to each singer until the performance begins. Erwin Schrödinger, who was hardly a stranger to quantum oddities, recognised how important this was and gave it the name that stayed. He regarded entanglement not as some minor technical nuisance, but as the characteristic trait of quantum mechanics, the thing that most sharply distinguishes it from classical ways of thinking. That is a strong statement, especially from someone whose name is attached to one of the central equations of the theory, and to a cat that has since suffered more metaphorical stress than any animal reasonably should. Schrödinger saw that when systems interact and then separate, the mathematics can leave them in a state where they cannot be fully described independently. Their realities are not simply stacked side by side. They remain intertwined in the description itself. A useful way to get a feel for this is to think about questions and answers, rather than objects and labels. Suppose two particles are prepared so that if both are asked the same question in the same way, their answers will be perfectly linked. Perhaps if one says up, the other says down. If you measure the first particle in a given orientation and get one result, then measuring the second in that same orientation gives the opposite result with certainty. That already sounds peculiar, but perhaps still manageable. One could imagine each particle carrying a hidden list of answers prepared in advance. If asked this way, answer up. If asked that way, answer down. Then the correlation would merely reflect prearranged instructions. The trouble begins when the possible questions vary. In quantum experiments, one can choose different measurement settings, different ways of interrogating the particles, and the resulting pattern of correlations is richer than a simple hidden answer sheet can reproduce if the answers must remain local and predetermined. The particles do not behave like students passing an exam with identical cheat notes tucked into their sleeves. The statistical pattern across many runs turns out to be too elegant and too strong for that. This is why entanglement is not just correlation, it is quantum correlation, and the distinction matters so much that it eventually became testable in Bell-type experiments. Before Bell enters the stage again, though, it is worth staying with the phenomenon itself. Why does entanglement feel so offensive to common sense? Partly because we are used to separation creating independence. If I take two cups from the same cupboard and place them in different rooms, they do not remain part of one mysterious cup state. Each cup is just a cup, deeply committed to its own local existence and usually minding its own business unless dropped. But in quantum mechanics, systems that have interacted can emerge in a state that is not merely a sum of separate local descriptions. The mathematics insist that there is more reality in the pair considered together than in the two pieces taken one by one. The whole, in a precise and not especially mystical sense, is not reducible to the collection of separately existing parts. This does not mean the particles stop being individual objects altogether. They can still fly apart, be measured in distant labs, strike different detectors, and go on participating in the ordinary practical life of experimental apparatus. What changes is the structure of the description. A classical physicist would like to say that once the particles are far apart, the complete story of the pair should amount to the complete story of particle 1 plus the complete story of particle 2, plus perhaps some shared history explaining any correlations. Entanglement says no, not always. Sometimes the shared state contains something that cannot be decomposed that way. Sometimes the pair remains one quantum system in the relevant sense, even across distance. This is why words like bond and link are tempting, though they can mislead if taken too literally. Nothing visible stretches between the particles. There is no tiny quantum ribbon quivering in the dark. The bond is not mechanical, it is informational and structural, though even those words need care because they can suggest a message being sent. In the standard quantum picture, entanglement does not involve one particle broadcasting instructions to the other every time a measurement is made. That would immediately trigger all the alarms of relativity. Instead, the shared state means that certain outcome patterns are built into the pair in a holistic way. When the measurements are compared later, those patterns emerge with a strength that local classical stories cannot match. There is something almost rude about this. The particles seem to preserve a kind of togetherness while denying us the neat mechanism we would prefer. If one imagines the universe as a network of local causes pushing and pulling in orderly sequence, entanglement behaves like an exception that refuses to look embarrassed. It says in effect that reality may not always be assembled from independently existing local facts in the way classical thought expects. And it says this while continuing to produce laboratory predictions of astonishing accuracy, which is the sort of behaviour that makes a theory difficult to ignore even when it is being conceptually unhelpful. At this point, a natural question arises. If entanglement is such a deep bond, why do we not notice it everywhere? Why are chairs not entangled with biscuits in any socially disruptive way? Why does the macroscopic world look so solid and separate if quantum systems can remain joined across distance? The short answer is that entanglement is both common and fragile. At the microscopic level, it arises quite naturally whenever systems interact. But maintaining clean, observable entanglement is difficult because interactions with the surrounding environment tend to spread and scramble the delicate quantum relationships. A particle interacting with air molecules, thermal radiation, nearby matter, detectors, fields, and all the rest begins to lose the kind of isolated coherence that lets entanglement show itself so clearly. This process is often discussed under the name decoherence, which sounds like a government report on a railway delay but is actually an important idea in modern quantum theory. Decoherence helps explain why the large-scale world does not usually display obvious quantum superpositions and long-lived entanglement in the blatant way that microscopic experiments can. The environment is constantly monitoring systems, in a sense, and the clean quantum phases that support striking interference and entanglement become effectively dispersed. So the everyday world regains a more classical appearance, not because quantum mechanics stops being true, but because the quantum relationships become buried under overwhelming environmental complexity. Reality, one might say, becomes less theatrical once enough air gets involved. Still, in carefully controlled laboratory conditions, entanglement can be created, preserved, and measured with extraordinary precision. Photons are especially useful for this because they can be generated in entangled pairs and sent to distant detectors while retaining their quantum correlations. Electrons, ions, atoms, and even larger systems can also be entangled under the right conditions. Experimental physicists have become remarkably good at this, which is both a triumph of technique and a slight worry if one was hoping entanglement would remain a minor philosophical curiosity. It did not. It became something laboratories could engineer, test, and even exploit. Indeed, entanglement is not just a conceptual headache. It has become a resource. Quantum information science uses entanglement in tasks like quantum cryptography, quantum teleportation, and quantum computing. Those phrases can sound fantastical, especially teleportation, which unfortunately does not involve sending oneself to another city in time for dinner. What it means in this context is that the state of one quantum system can be transferred to another using entanglement together with ordinary classical communication. Again, the universe preserves its habits. The strange bond is real, useful, and powerful, but it still refuses to let us send controllable signals faster than light. Every gift comes with administrative restrictions, yet even as technology learned to make practical use of entanglement, conceptual tension never fully disappeared. What exactly are we to say about two entangled particles separated by a large distance? Are they one system or two? Does measurement reveal a pre-existing relation, or help bring a definite outcome into being? Is the joint quantum state a complete description of reality, or a tool for organizing expectations? Different interpretations answer differently, and entanglement sits at the center of those disagreements like a quiet but immovable stone in the road. Some interpretations lean into the holistic nature of the state and accept that the world is not fundamentally made from locally independent facts. Others try to preserve realism by adding hidden variables, though Bell's theorem later limits how local such additions can remain. Still others propose branching worlds, relational accounts, or information-based views. Entanglement is compatible with many interpretive strategies, but it is never trivial in any of them. It is the point at which quantum theory most stubbornly resists being translated back into ordinary classical language. One reason the phenomenon feels so compelling is that it combines intimacy and distance in a way that our instincts rarely permit. We tend to think closeness enables connection, and separation weakens it. In entanglement, physical distance does not erase the joint structure. The particles can be sent far apart, and yet their measurement statistics still testify that they belong to one non-classical arrangement. This is not a sentimental togetherness. The particles do not miss one another. They do not exchange longing glances across the vacuum, but their shared state carries a form of relationship that remains meaningful even when the particles are no longer near. That alone is enough to make the old local worldview start checking its pockets. And yet one must keep saying it because the temptation to oversell is so strong. Entanglement is not simply magic influence across space. If you measure one particle, you do not gain the power to dictate the outcome of the other. The result you see is random from your local point of view. Only when the two sets of data are later brought together do the striking correlations emerge. This is why entanglement unsettles causality without straightforwardly overthrowing relativistic no faster than light signalling. The world behaves in a way that is less local than classical intuition prefers, but more disciplined than science fiction would hope. This strange middle ground is part of what made Einstein so uneasy, and Bell so important. Entanglement was the sore spot in the theory, the place where one could feel that something deep was at issue. If the particles were merely like the sock boxes, there would be no real problem. Hidden variables carrying predetermined answers would settle the matter neatly. But entanglement seemed to say the sockbox story was too simple, and Bell found a way to test exactly how simple it was allowed to be. Once that happened, entanglement stopped being only an interpretive puzzle and became a gateway to experimental verdicts about the structure of reality itself. For the moment, though, it is enough to feel the phenomenon before judging it. Two particles interact. They separate. And still the best quantum description treats them as parts of one shared state. One arrangement whose correlations outrun ordinary classical explanation. The pair is not just two little independent realities marching off in opposite directions with a folder of predetermined answers tucked under each arm. Something more unified remains in the mathematical and experimental story. Something that makes distance less decisive than it ought to be if locality and classical realism were the whole truth. That was the strange bond Einstein distrusted, Schrödinger named, and later generations learned to produce with lasers, crystals, detectors, and a truly heroic tolerance for calibration problems. It is the bond that turns a quiet question about distant influence into a serious challenge for physics. Because once you admit entanglement into the room, the next question arrives almost on its own. If the particles are not just carrying fixed local instructions, then what, if anything, is hiding underneath the quantum description? Could there still be unseen variables restoring order and locality behind the scenes? Or has entanglement already told us that the classical dream of a fully local underlying reality is on borrowed time? Once entanglement is on the table, a certain kind of hope appears almost automatically. It is the hope that the strangeness is only skin deep, that beneath the odd language of superpositions, probabilities, and unsettled properties, there lies a more familiar engine quietly doing honest work. Perhaps quantum mechanics is not wrong, exactly, but incomplete. Perhaps it is like a weather forecast that performs impressively, while still leaving out the actual position of every droplet in the cloud. Perhaps the blur in the theory reflects not a blur in reality, but only a blur in our access to it. This was the dream of hidden variables, and it was not the dream of cranks or eccentrics peering suspiciously at respectable physics from across the road. It was for a time a very natural dream, and for Einstein especially it looked less like wishful thinking than simple physical decency. The basic intuition is easy to understand. Quantum mechanics gives us probabilities for outcomes. It tells us, for example, that if a particle is measured in a certain way, There is some chance of one result and some chance of another. That can be read in two very different moods. In one mood, the probabilities are fundamental. The world itself does not contain a more precise answer before the measurement. Nature gives only the odds, and the specific outcome is not settled until the event occurs. In the other mood, the probabilities are signs of ignorance. The particle really does have a more detailed state, but the theory does not include it. If we knew the extra facts, the hidden variables, then the uncertainty would disappear, at least in principle. The coin would stop looking random because we would finally see the hand that flipped it. This second mood had enormous appeal because it fit an older and very powerful scientific habit. Classical physics had trained people to treat probabilities as placeholders for incomplete knowledge. If you cannot predict the path of smoke in the air or the outcome of dice on a table, that does not mean those systems are metaphysically undecided. It means you do not know enough about the microscopic conditions. There is disorder in the practical sense, but order underneath. The dream of hidden variables extended that habit into the quantum world. It said, in effect, perhaps the uncertainty is not final. Perhaps the quantum formalism is a brilliant summary of what happens when we average over deeper details we do not yet see. For Einstein, this was more than a technical possibility. It was a defense of realism. He wanted the world to contain actual physical properties whether or not anyone happened to be measuring them. If a particle exists, then it ought to have a real condition, not a ghostly cloud of mere potential outcomes waiting for a detector to force the issue. If two particles fly apart, then each ought to carry its own local state with it, not remain suspended in an unfinished joint description that only becomes definite when someone asks a question in a laboratory. Hidden variables offered a way to restore that picture. They promised that the world might still be made of definite local facts, even if the standard quantum theory only gives us an incomplete statistical view. There is something deeply attractive about that promise. It preserves a kind of independence in nature. Things can be what they are without waiting for observation. Distance can still matter. Explanation can still proceed by describing underlying states that evolve in time according to definite rules. The universe remains difficult, perhaps, but not coy. One can imagine why a physicist raised on classical clarity would prefer this to a theory that seems to blur reality until measurement. Even people who were less philosophically insistent than Einstein often felt the same pull. The idea that there might be a deeper layer beneath quantum mechanics was not absurd. In some ways, it was exactly what science had done many times before. Apparent randomness had been explained by unseen structure again and again. Why should the quantum case be different? At first glance, hidden variables seem especially persuasive in entanglement experiments. Suppose two particles are created together and then sent far apart. Later, each particle is measured in one of several possible ways. The outcomes are correlated. Well, then, perhaps the particles were simply issued matching internal instructions at birth. Not a sentimental birth, of course. More of a high-precision laboratory birth accompanied by equipment, probability amplitudes, and a technician trying not to spill coffee near the optics table. Still, the image is tempting. Each particle leaves the source carrying a set of hidden properties that determine how it will answer any measurement it may later face. No instant influence is needed. The correlation is already built in. Distance keeps its dignity. Relativity keeps its speed limit. Everyone gets to go home reasonably pleased. This sort of picture is often called a hidden variable theory, because the decisive details are not part of ordinary quantum mechanics. They are additional variables, extra facts, hidden not necessarily because nature is mischievous, but because our present theory does not track them. If those facts were known, the statistical haze would lift. The outcomes would appear as consequences of the full state, not as fundamentally random events. In that sense, the dream of hidden variables was a dream of completion. Quantum mechanics would remain useful, perhaps very useful, but it would cease to be the final word. It would become an effective theory sitting above a more detailed and more satisfying account of reality. Now, There were several ways this dream could be imagined. Some versions aimed to preserve both determinism and locality. In these versions, each particle carries all the instructions it needs, and nothing done far away can alter its local response at the moment of measurement. Other versions were willing to sacrifice strict locality, but retain realism and determinism. Those would come later in more serious form. But before Bell's theorem, many people who sympathized with Einstein naturally focused on the local kind. If the point was to avoid spooky distant influence, then the hidden variables had to live locally in the particles or in their shared common cause, not in some faster-than-light whisper travelling between laboratories. It is worth noticing how modest this can sound when stated carefully. The dream did not require magic. It did not require the rejection of experiment. It required only that quantum mechanics might be missing something. And science, after all, is full of theories that turned out to be incomplete without being worthless. Newtonian gravity is incomplete, but still astonishingly useful. Thermodynamics is not the final microscopic account of matter, but it remains indispensable. So when Einstein and others argued that quantum mechanics might be incomplete, they were not committing intellectual blasphemy. They were making a historically respectable move. The difficulty was that quantum mechanics was not merely useful. It was weird in a way that seemed increasingly resistant to classical improvement. Part of the resistance came from the work of mathematician and physicist John von Neumann, who early on presented arguments that many took to rule out hidden variable theories altogether. For a time, this discouraged interest in the subject. It created the impression that the matter had been settled by mathematical no-entry signs posted around the theory. But later scrutiny showed that the assumptions in those arguments were stronger than many people realized. The conclusion did not apply to every imaginable hidden variable model. It ruled out certain kinds, not all possible kinds. This matters because it reopened conceptual space. The dream of hidden variables was not dead. It had merely been told to sit in the corner for a while. A particularly important moment came with the work of David Bohm in the early 1950s. Bohm developed a hidden variable theory that reproduced the predictions of ordinary quantum mechanics, while giving particles definite positions guided by a quantum wave. This was a remarkable achievement because it showed, quite explicitly, that hidden variables were not impossible in principle. The world did not have to be fundamentally fuzzy in the way many had assumed. One could build an underlying deterministic model, but there was a catch, and it was not a small one. Bohm theory is non-local. The guiding structure depends on the configuration of the whole system in a way that allows distant settings to matter. So Bohm preserved realism and determinism, but not locality in the strict Einsteinian sense. That result was both encouraging and unsettling. Encouraging because it proved the standard story that hidden variables were mathematically impossible was too simple. Unsettling because the price of success seemed to be the very thing Einstein most wanted to avoid. The dream of hidden variables could survive, but perhaps not in the clean local form he hoped for. It was as though the universe said yes, you may have a deeper theory if you insist, but no, you may not have it without giving up that comfortable boundary between here and there. Still, before Bell's work, this issue was not yet fully sharpened. One could still imagine that some clever local hidden variable scheme might exist, some more subtle construction than the obvious instructionless picture. After all, quantum mechanics had already taught physicists not to underestimate the universe's talent for technical complications. Maybe locality and realism could still be rescued by a theory more ingenious than anyone had yet written down. Maybe the current form of the problem was only a sign that the right hidden variables had not yet been discovered. This is why the dream remained alive. It was not merely nostalgia, it was a live option, at least conceptually, and in some ways it felt almost inevitable that someone would try to formalize it. If two distant particles show correlations, then what exactly would a local hidden variable theory have to look like? What assumptions would it need? What statistical patterns would it predict? Could those patterns really differ from ordinary quantum mechanics in a testable way? These are the questions that eventually brought Bell to the centre of the story. But before that moment, the dream itself deserves some sympathy, because it arose from very deep instincts about what a world ought to be. One of those instincts is that explanation should go beneath appearances. If a thermometer reading jumps around, one looks for molecular motion. If planetary motion seems irregular, one searches for gravitational dynamics. If quantum outcomes look random, one wonders whether there is an unseen level below the theory. Another instinct is that objects should have properties independently of observation. A moon does not cease to have a position because no one is looking at it. A stone does not become indecisive about its weight in the absence of a scale. Hidden variables were a way of extending that instinct downward into the microscopic world. The particles may seem probabilistic, but that is because we have not yet learned the whole truth about them. And then there is locality, the instinct that what happens in one place should depend on local conditions, not on remote decisions made too far away for any physical influence to arrive in time. This instinct is strengthened, not weakened, by relativity. Once Einstein had taught physics to respect the structure of space-time so rigorously, it became even harder to accept a theory that seemed to let distant choices participate in defining local outcomes. Hidden variables promised to keep faith with that structure. They offered a world in which particles carry their own reality with them, and measurements simply uncover it. You can think of the dream this way. Imagine two distant observers, each equipped with a measurement device that can be set in different ways. A local hidden variable theory says that before any measurement occurs, the relevant facts are already there. The shared source gives each particle a complete local package, perhaps correlated with its partner, perhaps determined by some common variable from the past. When the measurement is chosen, the particle consults only its local state and the local device setting to generate an answer. No rush of influence across space, no last-minute adjustment based on the distant choice. The world remains orderly in the classical sense. All the mystery lies in our ignorance of the hidden package. The elegance of this picture is obvious. It turns quantum measurement into revelation rather than creation. It makes probability epistemic rather than ontological, a reflection of knowledge rather than being. And it restores the comforting idea that the world does not wait for us to ask questions before deciding what it is. One can see why Einstein found such a view preferable to a formalism that seemed to make observation central. Science, in his eyes, should not become a theory of what happens when humans arrange apparatus. It should be a theory of what exists. Yet there was always a lurking difficulty. To reproduce the full range of quantum correlations, the hidden variables would need to coordinate answers for different possible measurement settings, including settings chosen later and independently at each side. If the particles are to remain local, then each answer must be generated without knowledge of the distant setting. That means the hidden package must contain enough prearranged structure to cover every possible local question while still matching the quantum patterns when the data are later compared. This is where the dream starts to strain. The more settings one allows, the more exacting the coordination must become. The particles begin to resemble actors handed extraordinarily detailed scripts for every possible branch of an interactive play. Still, even that did not obviously prove the dream impossible. Nature is allowed to be complicated, and hidden variable enthusiasts could always say that the deeper theory might be intricate in ways the surface-level quantum formalism hides. What mattered was not whether the model felt cumbersome in imagination, but whether its predictions could, in principle, match experiment. If they could, then realism and locality might yet survive together. This was the point at which the dispute became ripe for transformation. For years, the debate between Einstein and the more orthodox quantum camp had the flavour of a profound but slightly suspended philosophical argument. One side said the theory is incomplete because it lacks definite local reality. The other said that demand misunderstands what the theory is for. One side wanted hidden causes, the other wanted conceptual discipline about measurement and observables. It was serious, certainly, but many working physicists could avoid it while still getting useful work done. If you were busy calculating spectral lines, building detectors, or figuring out how not to electrocute yourself with laboratory equipment, questions about the ultimate furniture of reality could be postponed. What the dream of hidden variables needed, if it was ever to advance beyond a quarrel of intuitions, was a test. Not a general sense that one picture feels nicer than another, not a conference debate in which Bohr speaks in layered paragraphs, and Einstein stares at him with patient disapproval. It needed a way to say this kind of world predicts these statistical limits, while quantum mechanics predicts something else. Then the matter could leave the seminar room and enter the laboratory, where photons are less impressed by rhetoric. That is what made the dream so important even before it was judged. It forced physics to articulate what it meant by locality, by realism, by completeness. It compelled people to ask whether probability in quantum mechanics reflects ignorance or reality itself. It sharpened the distinction between a universe that merely appears indeterminate and one that is indeterminate in a more profound sense. And it created the conceptual space in which Bell could later do something extraordinary. He could take Einstein's hope for local hidden variables seriously enough to derive consequences from it. There is a quiet irony in that. Bell was not mocking the dream. He was honouring it by giving it mathematical form. He asked what would follow if the world really were built that way. If hidden variables exist and remain local, then certain correlations must obey certain constraints. If experiments violate those constraints, the dream in its local form cannot be right. This was not a philosophical shrug. It was an invitation to reality to answer. So the hidden variable dream stands in the story not as a foolish detour, but as a necessary aspiration. It was the last great effort to preserve a classical style of underlying order beneath the quantum surface. It said perhaps nature is still local, still definite, still complete in the way Einstein hoped, and we have simply not yet found the deeper map. The beauty of that dream is that it did not rest content with being emotionally satisfying. It was willing to be tested. And once that willingness entered the picture, the next step became unavoidable. Someone had to ask with absolute clarity what kind of statistical world a local hidden reality would actually produce, and whether the universe was prepared to live within those limits. The remarkable thing about John Bell is that he did not enter this story as a theatrical rebel announcing that he would overturn the foundations of physics before lunch. He arrived more quietly than that, and perhaps that is fitting, because the most consequential changes in science do not always begin with trumpets. Sometimes they begin with a person reading an old argument and deciding, with unusual clarity, that the argument deserves to be taken seriously enough to test. Bell looked at the long and often frustrating dispute between Einstein and the defenders of orthodox quantum mechanics, and saw that something important had been left hanging in mid-air. People had debated what quantum theory meant. They had argued about locality, reality, measurement, completeness, and all the other words that tend to make physicists either very animated or slightly evasive depending on the hour. But Bell asked a different kind of question. He asked what follows if Einstein was right in a certain precise sense, not emotionally right, not philosophically noble, right in a way that has measurable consequences. That shift changed everything. Up to that point, much of the argument about hidden variables had the flavour of a very serious, unresolved family disagreement. Everyone knew it mattered. Everyone had strong views. Many people had memorised their preferred lines. But a large portion of working physics could continue quite happily without deciding the matter. Quantum mechanics predicted outcomes with astonishing success. Engineers built devices, experimentalists built apparatus. Theoretical physicists did what theoretical physicists do, which is think deeply, write symbols, and occasionally look like they have just remembered an unfinished argument from 10 years earlier. Meanwhile, the debate over whether the theory described reality itself or merely the outcomes of measurements remained important and strangely suspended. Bell refused to let it remain suspended. To appreciate the force of his contribution, it helps to remember exactly what he inherited. Einstein and others had argued that the quantum description of entangled systems seemed incomplete. If two particles move far apart and measuring one allows a certain prediction about the other, then either the distant particle had that relevant property all along, or else something disturbing is happening across space. Einstein preferred the first option. He wanted a local underlying reality in which distant systems possessed definite states independent of one another, apart from whatever common cause they share in the past. Bohr and many others resisted the argument and defended the quantum formalism, though often in language that could leave a reader feeling as though they had entered a conversation already halfway through, and somehow missed the key nouns. What was missing was a clean way to decide whether a local hidden variable picture could actually reproduce the predictions of quantum mechanics, not just in a general impressionistic sense, but in a mathematically exact one. Could a theory in which each particle carries local predetermined properties generate the same pattern of correlations that quantum mechanics predicts for entangled pairs? This was the question Bell sharpened. He did not start by declaring locality impossible. He started by giving locality and hidden variables their best chance. He asked what kind of statistical structure must hold if the world really is built that way. There is a kind of fairness in that approach. Bell was not ridiculing Einstein's concern. He was formalizing it. He was saying, let us suppose, for the sake of argument, that each particle has a complete local state, possibly influenced by some shared hidden factor from their common origin. Let us suppose that the result on one side depends only on the local measurement setting, and on that shared hidden information, not on any choice made at the distant detector. Let us suppose, in other words, that the world keeps its local manners. Then what? The answer turned out to be that such a world would place strict limits on the strength of correlations that distant measurements can display. Quantum mechanics predicts correlations that go beyond those limits. That is the essence of Bell theorem, and once that was understood, the old argument was no longer sheltered inside philosophy. It had become empirical. If experiments agree with the quantum prediction, then no theory that combines local hidden variables in the straightforward Bell sense can be the full story. Local realism, at least in that form, fails. It is difficult to overstate how powerful that move was. Bell took a debate that had been clouded by interpretation and turned it into a question nature could answer. He showed that locality together with hidden predetermined values is not just one interpretation among many. It is a class of theories with testable consequences, and those consequences differ from the standard quantum ones in measurable ways. This is why Bell's name carries such weight. He did not merely add another opinion to the pile. He built a bridge between foundational philosophy and laboratory physics, and once that bridge existed, people could no longer pretend the question was only about taste. The elegance of Bell work lies partly in how modest the ingredients are. He did not need to invent exotic new particles or demand impossible technologies from the outset. He looked at pairs of entangled particles and imagined measuring each one in one of several possible ways. If the outcomes are determined by hidden variables already carried by the particles, and if each outcome depends only on local conditions, then the average pattern of agreement and disagreement across many runs must satisfy a certain bound. That bound is what later came to be called a Bell inequality. The details can be written in neat mathematical form, but the heart of it is simple enough to say in words. In a local hidden variable world, there is only so much correlation you can squeeze out of prearranged instructions. Quantum mechanics says nature sometimes squeezes out more. A useful image is that of two students sitting an exam in separate rooms. They have had a chance to coordinate beforehand, but cannot communicate during the test. If the questions they may face come from a known list, then they can prepare a strategy in advance. They can agree what answers to give under each possible condition. Bell asked, in effect, what is the best score such a local prearranged strategy can achieve if the pattern of questions varies? There is a ceiling. No amount of clever planning gets you past it if there is truly no communication during the exam, and the answers are fixed locally in advance. Quantum entanglement behaves as though the students somehow exceed that classical ceiling, not by cheating in the ordinary sense, and not by sending a signal in a useful, controllable way, but by living in a statistical world unlike the one classical coordination allows. This is the point at which many people attempted to leap straight to dramatic conclusions, instant influence, the end of relativity, cosmic telepathy for photons. It is best to resist all that, at least for the moment. Bell theorem does not say that faster-than-light signalling has been achieved. It does not say one observer can send a message to the other merely by choosing a measurement setting. What it says is subtler and, in some ways, more unsettling. It says that the correlations observed between entangled systems cannot be explained by any theory in which outcomes are fixed by local hidden variables alone. Something in the old package has to give, either locality in the strict Bell sense, or the idea that outcomes are locally predetermined in that classical way, or some other assumption woven into the setup. That last point matters because Bell theorem is often summarized too loosely. People say it proves the universe is non-local, full stop. But Bell himself was more careful, and one should be careful with him. The theorem shows that no local hidden variable theory can reproduce all the quantum predictions. Many physicists do take that as strong evidence that nature is non-local in some meaningful sense. Others emphasize that what fails may be a certain combination of locality with a particular realist picture of pre-existing outcomes. Still others explore interpretations where the notion of a single outcome or of independent observer neutral facts is handled differently. The theorem does not settle every interpretive question. What it settles is that Einstein's dream of a local hidden completion of quantum mechanics cannot survive untouched. And this is exactly why the question changed everything. Before Bell, one could still hope that the conceptual dispute might dissolve in one direction or the other without experimental drama. Perhaps quantum mechanics would someday be replaced by a deeper local theory. Perhaps the old realist worries would fade as physicists became more accustomed to the quantum formalism. But after Bell, the stakes became sharper. If experiments violated Bell inequalities in the way quantum mechanics predicts, then the local hidden dream would not merely be unfashionable, it would be wrong. Nature herself would have taken sides, though not in a way guaranteed to make anyone entirely comfortable. Bell arrived at this conclusion in the 1960s, a time when quantum theory was already well established in practice, but its foundations were still, in many quarters, treated with a curious mixture of reverence and avoidance. Foundational questions had a reputation for being dangerous to one career, and possibly bad for one's social standing at conferences, rather like bringing up inheritance laws at a wedding. Bell pursued them anyway. He was interested in the conceptual structure of the theory, and dissatisfied with the way some people dismissed Einstein objections as though the matter had already been settled by style rather than argument. That intellectual honesty is one of the reasons Bell remains so respected. He did not accept the standard story just because it was standard. He wanted to know what followed if one examined it carefully. There is also something refreshingly concrete about the way he proceeded. He did not solve the problem by philosophical rhetoric or by producing a grand interpretation of everything. He found a constraint. If local hidden variables govern the outcomes, then certain correlations cannot exceed a specific limit. Quantum mechanics predicts that, for suitable entangled states and measurement choices, the limit will be exceeded. The result is not a vague suggestion. It is a difference in statistical expectations. That is a scientist's favourite kind of disagreement because it can be fed to an apparatus. The concept of a Bell inequality can sound intimidating when first encountered, especially because the phrase inequality belongs to mathematics and can make perfectly sensible people suspect they are about to be ambushed by blackboard symbols. But the important content is quite intuitive once one strips away the formal clothing. Bell found a way of comparing different patterns of measurement results such that any local hidden strategy must obey a certain relation among them. It is rather like discovering that if a person insists they always walk locally from room to room without cutting through walls, then their route lengths must satisfy certain constraints. If you later observe route statistics that violate those constraints, You do not merely conclude the walking was brisk. You conclude that the original local picture of movement was wrong or incomplete. In Bell's case, the violation is not by a small technical margin that only a committee could love. It is clean and principled. Quantum mechanics predicts it directly. The extraordinary part is that the theory had been carrying this implication all along, hidden inside its treatment of entanglement, waiting for someone to ask the right question. Bell asked it. That is why his theorem feels less like an invention, and more like a revelation of what quantum mechanics had been trying to tell people from the start, while they argued about whose philosophy deserved the better chair. Of course, Bell's theorem on paper was only the beginning. A theorem does not become part of the furniture of science until experiments confront it. At first, this was not easy. The measurements required careful control, clean entangled states, rapid switching of detector settings, and all the rest of the practical heroism experimental physics demands from people who spend large portions of their lives persuading stubborn equipment to behave. But even before the decisive experiments were done, Bell had already transformed the conceptual landscape. The question was now unavoidable. Is the world Bell local or not? If not, what exactly fails? And what does that tell us about reality? One reason the theorem had such impact is that it restored seriousness to foundational physics. It showed that the old debates were not merely philosophical wallpaper, they had physical bite. Einstein was not just expressing a vague discomfort. He was pointing toward a structural tension, and Bell found the lever that made the tension measurable. In that sense, Bell did a service not only to quantum theory, but also to scientific reasoning itself. He reminded physics that conceptual clarity matters, that one can take big questions seriously without drifting into empty speculation, and that sometimes the most profound experiments begin with someone refusing to be satisfied by a slogan. There is a gentle irony in the fact that Bell's theorem pleased almost no one completely. If you were strongly committed to local hidden variables, the theorem threatened your position. If you were happy with standard quantum orthodoxy and preferred not to revisit the old Einstein complaints, Bell forced you to notice that the theory really does challenge classical locality in a way not easily brushed aside. If you hoped for a neat resolution in which all parties could keep their favourite intuitions, Bell politely removed that option from the shelf. The world would not permit it. That is often how progress works in foundational science. It does not hand you a more comfortable picture. It removes the pictures you were no longer entitled to keep. Still, Bell was not a prophet of despair. There is something deeply satisfying about his result precisely because it is so clean. Reality may be strange, but Bell showed how to ask the strangeness a disciplined question. He did not turn mystery into mysticism. He turned it into an experimental criterion. That is one of the noblest things physics can do. It can take a discomfort that sounds almost metaphysical and turn it into a table of numbers gathered by tired people in dark laboratories full of optics and cables. There is a beauty in that, a very practical beauty. This sort that makes science feel less like a collection of facts and more like an ongoing negotiation with the universe. It is also worth pausing over the emotional change Bell introduced. Before his work, Einstein's hope for hidden variables could still be held as an open possibility without immediate embarrassment. After Bell, that hope had to become more selective. One could still pursue hidden variables, but not local ones of the simple Einstein style. One could still preserve realism, perhaps, but only by paying a price elsewhere. Bohm theory, for instance, would later stand as a clear example of a hidden variable theory that survives by embracing non-locality. Many worlds would preserve the quantum formalism while handling outcomes in a different way. Relational approaches, information-centered interpretations, and other views would continue the struggle. Bell did not end interpretation. He made it impossible to ignore the cost of one's preferred interpretation, and that is why his question changed everything. It forced a decision about what kind of universe we are willing to say we inhabit. A universe of local pre-existing properties can no longer be maintained in the straightforward classical way if the experiments agree with quantum theory. A universe described by quantum mechanics contains a deeper pattern of connection, one that cannot be mimicked by local hidden scripts. The old language of separate things carrying separate facts through separate regions of space no longer does all the work. The world is, in some sense, less separable than it looks. Bell did not tell us exactly how to picture that world. He told us which picture fails. There is tremendous value in that. Sometimes knowing what cannot be true is the most honest advance one can make. In the history of science, many revolutions proceed by subtraction. The Earth is not the centre. Time is not absolute. Space is not a passive stage. Light is not just a wave. Quantum outcomes are not governed by local hidden variables of the Bell kind. Each removal narrows the space of respectable belief and pushes us toward a stranger but more accurate understanding. As the story continues, the next natural step is to look more closely at the structure Bell uncovered. How can an inequality, a simple bound on statistical patterns, carry such enormous weight? How can something that sounds so dry become a verdict on locality, realism, and the limits of classical explanation? This is where the mathematics of the theorem, even when translated carefully into ordinary language, starts to show its sharpness. Bell did not merely say quantum mechanics is weird. He showed how weird it must be if it is right, and how to recognize that weirdness in the data. That is where the argument leaves the broad philosophical stage and enters the precise logic of testing reality itself. What made Bell's results so powerful was not only that it challenged an old hope, but that it did so with unusual restraint. Bell did not announce that reality was broken, or that relativity had failed, or that physicists should immediately begin speaking in hushed tones about cosmic mystery while staring into the middle distance. He did something more disciplined than that. He found a way to turn a vague philosophical disagreement into a numerical test, and that is one of the most important shifts science can make. When a deep question stops being a matter of preference and becomes something you can ask the world directly, the whole conversation changes. At first, the phrase Bell inequality sounds dry enough to send even a reasonably curious person drifting towards sleep, which in our present circumstances may not be an entirely unwelcome side effect. It has the flavour of a technical footnote, something tucked into the back of a paper where the real excitement is presumed to be elsewhere. But in this case, the footnote is the excitement. The inequality is the hinge on which the whole argument turns. It is the reason physicists could stop arguing in circles about locality and hidden variables, and instead build experiments to see which picture nature was willing to support. The basic idea begins with a very modest question. Suppose the world really is local in the way Einstein hoped. Suppose that when two particles fly apart, each carries with it a complete set of hidden instructions, enough to determine the answer it will give to whatever measurement it later faces. And suppose also that what one particle does depends only on those local instructions and on the local measurement chosen in its own laboratory, not on some distant choice made elsewhere. If all that is true, then there should be limits on how strongly the measurement results can be correlated when the data from both sides are compared. That may sound almost too obvious to matter, but it matters enormously. Because once you assume the particles are answering from local pre-written instructions, you can begin to reason about what kinds of patterns are possible and what kinds are not. You do not need to know the exact hidden details. You only need to know that the answers are locally fixed in advance. From that alone, Bell showed, a ceiling appears. There is a maximum strength of correlation that no local hidden variable story can surpass. If actual experiments exceed that ceiling, then the local hidden variable picture cannot be right. It is worth sitting with the sheer elegance of that for a moment. Bell did not need to know what the hidden variables are. He did not need to specify whether they are little numbers tucked inside the particles or miniature instruction manuals written in very small print by a universe with excessive confidence in paperwork. He only needed the general structure, local answers, shared hidden cause in the past, no dependence on the distance setting at the moment of measurement. those assumptions are enough to impose a bound, and that bound is what the inequality captures. A good way to feel how this works is to imagine not particles for a moment, but two separated contestants playing a coordination game. They are placed in different rooms and cannot communicate once the game begins. Before they are separated, they are allowed to agree on a strategy. Later, each contestant is asked one question chosen from a small menu of possible questions. Their goal is to produce answers that match or differ in certain required ways so that, when many rounds are scored, their overall coordination is as strong as possible. Because they cannot talk during the game, all they have is their pre-arranged plan. Now, if the menu of possible questions is limited, they can certainly do fairly well. They can agree in advance how to answer each possible question. If one is asked question 1, answer yes. If asked question 2, answer no. The other contestant prepares a matching or opposing list depending on the rules. Across many rounds, their performance will reflect the best classical strategy available. But there will still be a limit. No matter how cleverly they prepare, certain combinations of possible questions will expose the fact that they cannot coordinate beyond a certain point without communication during the game. Their advanced planning has a hard ceiling. Bell's insight was that entangled particles can be put into a mathematically analogous situation. Each particle is measured in one of several possible ways. Each measurement produces one of two possible outcomes. If the outcomes are determined by hidden local instructions, then the statistics of agreement and disagreement across the different choices of measurement must obey a certain overall constraint. The inequality is that constraint. It is, in essence, a bookkeeping rule for any world built from local prearranged answers. What makes this remarkable is that quantum mechanics predicts a violation of that rule. Not a tiny violation that only emerges after philosophers have argued over decimal places, and experimentalists have developed eye twitches from too much calibration, but a clear systematic one. The entangled particles behave as though their coordination exceeds what any classical local strategy can provide. They do not just act correlated, they act more correlated than local hidden instructions allow. This is the moment where the inequality becomes something much larger than a mathematical curiosity. It becomes a witness. It tells us whether the world can be described as a collection of distant objects carrying local, definite answers from a shared past. If the inequality is obeyed, that picture might still survive. If it is violated, that picture fails. The beauty of such a test is that it does not depend on rhetoric. One side cannot win by sounding more profound. Another cannot win by announcing that ordinary language is inadequate, and then leaving everyone to sort out their feelings in the corridor afterward. The apparatus does not care who gave the better conference talk. It produces counts, coincidences, detector clicks, and statistical patterns, and those patterns either fit inside the local bound or they do not. To understand why an inequality is the right kind of tool here, it helps to remember that Bell was not trying to prove quantum mechanics from scratch. Quantum mechanics was already successful. The question was whether some deeper local account could sit underneath it and reproduce the same observable results. Bell's answer was that if such a local deeper account exists, its statistical predictions cannot be completely identical to those of quantum mechanics. Somewhere, in the pattern of outcomes, there must be a difference. The inequality marks where that difference lives. One way to picture it is to imagine a fence built around a whole family of possible worlds. Every world in that family shares the same essential character. Outcomes are predetermined by hidden variables. Each outcome is local. Correlations come only from shared history, not from instant distant influence. Bell's inequality is like the boundary of that fenced region. Any theory with those features must stay inside. Quantum mechanics predicts that entangled systems sometimes land outside the fence, so when experiments agree with that prediction, they are not merely supporting one theory over another in the usual way. They are showing that the world itself does not live inside that local hidden region. This is also why Bell's result felt so unsettling to many physicists. It did not simply say quantum mechanics is odd. Everyone already knew quantum mechanics was odd. It said the oddness has teeth. The classical hope of explaining entanglement with local pre-written answers is not just aesthetically strained. It is statistically impossible if the experimental results continue to follow the quantum pattern. The universe is not merely surprising, it is excluding a whole style of explanation. There is a subtlety here that deserves care. The inequality does not require us to know what happens in any single run of an experiment. In one trial, the outcomes may look unremarkable. A detector clicks here, another clicks there. Nothing about a single event screams that reality has crossed a philosophical border. The power lies in repetition. Run the experiment again and again with different measurement choices, collect the outcomes, compare the rates of agreement and disagreement, and only then does the hidden structure emerge. This is very much in the spirit of physics. Many deep truths are not visible in one isolated event. They reveal themselves through patterns, through distributions, through the way nature behaves over many careful trials. That may also be one reason the result feels a little eerie. We are used to thinking that reality ought to declare its character in individual happenings. A ball either lands in the basket or it does not. A light is either on or off. But Bell-type tests tell us something different. The character of the world, local or not in the hidden variable sense, is written into the long-run statistics of many tiny events. It is not one click that settles the issue, but the accumulated rhythm of thousands or millions of them. Reality on this question speaks as a chorus rather than a soloist. This also helps explain why the theorem had to wait for the right experimental era to be fully tested. It is one thing to propose that certain correlations should exceed a classical bound. It is another thing entirely to generate clean entangled pairs, choose measurement settings appropriately, record outcomes efficiently, and rule out every ordinary way the data might mislead you. Bell gave physics the conceptual measuring stick. Experimentalists then had to build the world's most patient laboratories around it. Before we get to those experiments, though, it is useful to stay with the logic a bit longer, because there is something philosophically profound about the fact that an inequality can test reality at all. Normally, we think of reality as being tested by direct properties. Does this particle have this mass? Does that planet follow this orbit? Does this material conduct electricity? But Bell's inequality tests not a simple property, but a possible structure of explanation. It tests whether the world can be understood as local hidden variables all the way down. That is unusually deep. It is not merely checking a numerical prediction. It is interrogating the grammar of causation, and inequalities are especially suited to this because they capture limits. They tell us not exactly what every local hidden theory predicts in detail, but what none of them can exceed. This is often more powerful than a direct model-by-model comparison. If I invent one particular local theory and it fails, someone else can always invent another. But if Bell shows that every theory in a broad class must satisfy a certain bound, then violating the bound rules out the whole class at once, that is a very strong kind of result. It turns a sprawling debate into a sharp exclusion. There is something almost courtroom-like about it. Bell is not asking each hidden variable theory to come forward one by one and explain itself individually. He is establishing that any theory meeting the relevant conditions must obey a general law of behaviour. Once the data violate that law, the entire family loses its case. They may protest, of course. They may try to challenge one of the assumptions, and later many people would do exactly that. But the original simple hope that local hidden instructions can explain entanglement in a classical way is no longer available. Of course, the moment one says this, another question arises. If the inequality is violated, what exactly must be abandoned? Is it locality? Is it realism? Is it the idea that measurement choices are independent? Is it the notion that outcomes are single definite events in the classical sense? Bell's theorem itself does not force every interpretation into one single sentence. It tells you that you cannot keep the whole package. Something in that package must go. Different interpretations choose different sacrifices. That is part of why the theorem remains central to philosophy of physics, and not just to experimental design. Still, from the point of view of Einstein's original hope, the message was stark. The world cannot be both locally causal in the classical hidden variable way and still reproduce the quantum correlations. The dream of explaining entanglement by saying the particles simply left the source with matching instruction sheets had run into a wall. That wall was not built out of metaphysical disdain. It was built out of mathematics and then checked by experiment. You might think this makes Bell's result feel cold, but in another sense it makes it strangely intimate. Here's a tiny event in one detector and another tiny event in another, perhaps far away, and by gathering enough of them we find that reality refuses to behave like a collection of separate local scripts. The particles are not chatting in the ordinary way. They are not sending secret messages faster than light that we can hijack for practical use, but they are participating in a structure of correlation that surpasses what local prearrangement permits. That is a very peculiar thing for the universe to do, and an inequality is what lets us say so with discipline rather than awe alone. There is also a lesson here about how mathematics functions in physics. People sometimes imagine mathematics as an ornamental language for dressing up conclusions reached elsewhere. Bell's inequality shows the opposite. Mathematics here is not decoration. It is the instrument that reveals which explanatory worlds are possible and which are not. Without the inequality, one can argue forever about whether local hidden variables feel plausible. With it, plausibility becomes answerable. The theorem extracts a physical commitment from the philosophical picture and turns it into a statistical consequence. That is an extraordinary act of translation, and like all good translations, it preserves the spirit while clarifying the content. Einstein wanted local hidden variables because he believed distant things should possess their own reality, independent of remote measurements. Bell asked what that would statistically imply for entangled systems. The inequality is the answer. It is the shadow that locality and hidden variables cast into the space of observable data. Once you know the shape of that shadow, you can compare it with the real shadow nature produces. If the shapes do not match, the object you imagined is not the one standing there. Perhaps that is why Bell's theorem remains so haunting, even to people who do not spend their time adjusting photon sources or debating interpretation after conferences. It tells us that some of the deepest assumptions of classical common sense can be confronted in a finite experiment. We do not have to be satisfied with asking whether the universe is strange in some vague poetic way. We can ask whether the strangeness exceeds a local bound. We can ask whether separate things really are separate in the manner we once imagined, and we can get a measurable answer. By this point in the story, the stage is set for the experimental drama. The inequality is ready. The theoretical difference between local hidden variables and quantum mechanics is clear. What remains is the difficult, unglamorous, and ultimately magnificent work of making entangled particles behave well enough for the test to be convincing. That meant photons, polarizers, detectors, timing systems, measurement choices, and the slow, patient closing of every loophole that critics could reasonably point to. Because once an inequality has given you a way to test reality, the next task is to make sure reality is not being impersonated by a faulty detector, a lazy switch, or a piece of apparatus having one of those days that experimentalists know too well. Of course, an inequality on paper is only half a revolution. The other half belongs to the people who must persuade the physical world to answer it clearly, and the physical world, for all its grandeur, is often a rather fussy experimental partner. Bell had shown that local hidden variable theories and quantum mechanics part company in a measurable way. But to turn that insight into something more than a beautiful argument, physicists had to build experiments that could actually test the difference. That meant finding real systems, real particles, real measurement choices, and real detectors capable of gathering enough clean data to decide whether nature stays inside the classical limit or steps beyond it. This is where photons entered the story in a starring role, and one can hardly blame experimentalists for choosing them. Photons are the particles of light, and they come with several practical advantages. They move fast, which is useful when distance and timing matter. They can be generated in correlated pairs under controlled conditions. Their polarization, the orientation of the electric field associated with the light wave, provides a convenient property to measure in different ways. And perhaps most importantly, photons have the decency to travel through apparatus without requiring the kind of emotional support some other particles seem to demand. They are not always easy, of course. No experimental system is easy once you ask it to settle the foundations of reality, but photons were, and remain, among the best tools for this kind of work. The central idea of these experiments was simple in outline and demanding in detail. Create a pair of entangled photons, send them in opposite directions toward distant measurement stations, choose how to measure each photon, record the outcomes, and repeat this over and over until the statistical pattern becomes clear. If the world is governed by local hidden variables of the Bell sort, then the correlations between the outcomes must remain within the Bell limit. If quantum mechanics is right, the correlations will violate that limit. The experiment, then, is a kind of repeated question asked to the universe. Are these photons merely carrying local pre-written instructions, or is something less classically separable going on? Now, when said that way, the experiment sounds almost straightforward, which is a dangerous impression to allow anywhere near a laboratory. In practice, everything mattered. The source of entangled photons had to be reliable, the measurement settings had to be chosen and implemented precisely, the detectors had to register events faithfully, the timing had to be good enough to identify which photon on one side belonged with which photon on the other. Background noise had to be controlled, statistical errors had to be managed. One begins to appreciate that experimental physics is not just the art of measuring things, but the art of preventing the rest of the universe from being unhelpful while you do so. The first great experiments grew out of this practical struggle. In the late 1960s, Bell had given the world a theorem. In the early 1970s, physicists began trying to confront that theorem directly. One of the most important early efforts came from John Clauser, together with collaborators including Stuart Friedman. Clauser was one of the people who took Bell results seriously enough to ask not only what it meant, but how one could actually test it in the real world. That required translating Bell's abstract reasoning into a form usable with realistic detectors and photon sources. It is one thing to prove a theorem in ideal conditions. It is another to build a machine in a room full of wires and optics, and then ask that machine to perform the theorem with sufficient grace. Clauser and others developed experimentally accessible versions of Bell-type inequalities suited to actual photon measurements. Then came the challenge of producing entangled photons. One common method in the early era used what is called an atomic cascade. A suitably excited atom can emit two photons in succession as it drops through intermediate energy levels. Under the right conditions, the polarizations of those photons are entangled. That gave experimentalists a source, not perfect, but workable. The photons could be sent toward polarizers on opposite sides, and by rotating those polarizers to different orientations, one could test how often the results agreed or disagreed. Polarization itself is a wonderfully useful property, because it allows a very tangible picture without being too misleading. If you pass ordinary polarized light through a polarizing filter, the amount transmitted depends on the relative orientation of the light's polarization and the filter. For single photons in Bell tests, the situation is more discrete. A photon either passes or does not pass, depending probabilistically on the measurement arrangement. When entangled pairs are used, the joint pattern of passing and not passing on the two sides carries the correlation structure of interest. Vary the polarizer angles, collect enough coincidence counts, and the Bell test comes to life. The Friedman and Clauser experiment in the early 1970s was one of the first landmark realizations of this program. It did not settle every possible concern forever, but it was a major breakthrough. They measured correlations between entangled photons and found agreement with quantum mechanics rather than with the local hidden variable bound they were testing. For the first time, Bell's idea was not just a theorem waiting for a stage. It had become experimental evidence. Nature, when asked through a carefully arranged optical setup, appeared to side with quantum theory. This was an extraordinary moment, though it did not instantly silence everyone, because physics is healthier when it keeps some skepticism in reserve. The early experiments had limitations. Detection efficiency was not high. Certain assumptions had to be made about the subset of detected events representing the whole. The settings on the measuring devices were not switched rapidly while the photons were already in flight. All of this left room for what became known as loopholes, possible ways a determined local realist might argue that the experiments had not yet fully excluded all local hidden variable explanations. But the broad significance remained. The first great experiments had opened the door and shown that Bell's theorem was not trapped in thought experiment territory. It could be tested, and the results were leaning in a distinctly quantum direction. If one imagines the atmosphere around this period, it must have been a curious mixture of excitement and caution. On one hand, here was direct experimental contact with one of the deepest conceptual problems in physics. On the other hand, the instruments were not yet perfect, and foundational questions are never more lively than when the data are impressive, but not yet able to satisfy every critic. There is, after all, a long and respected tradition in science of saying yes, very interesting, but have you ruled out the annoying alternative? Experimentalists, to their credit, generally do not take that as a personal insult. They take it as a job description. This is one reason Alain Aspect became such a central figure in the next phase of the story. In the early 1980s, Aspect and his colleagues in France carried out a celebrated series of experiments that greatly strengthened the empirical case against local hidden variable theories. Like the earlier work, these experiments used entangled photons and polarization measurements, but they pushed the design further in ways that mattered conceptually as well as technically. The goal was not merely to repeat the Bell test, it was to tighten it, to make it harder for locality-friendly explanations to slip through available cracks. One of the most important issues concerned the measurement settings themselves. In Bell-type reasoning, the choice of how to measure each photon should be independent and should not be able to influence the distant particle through any slower-than-light mechanism before the measurement is completed. If the settings are fixed long in advance, one can worry, at least in principle, that some shared hidden variable at the source has already accounted for them. To press the locality issue more sharply, one would like to change the settings while the photons are already on their way, fast enough that the choice made on one side cannot be known on the other side by any signal moving at or below the speed of light before the measurements occur. Aspect's experiments moved in this direction. In one particularly famous version, the measurement settings were switched during the flight of the photons. This was not yet the final word, but it was a powerful step. It meant the photons could not simply have left the source carrying instructions tailored to a single, fixed pair of detector orientations known from the start. The experimental arrangement was becoming more dynamic, more faithful to the spirit of Bell's locality requirement. The universe was being asked a harder question. The technical means of doing this switching were themselves a triumph of ingenuity. Fast optical switches, timing electronics, and carefully separated measurement stations had to work together with enough precision that the relevant events remained space-like, separated in the relativistic sense. That phrase means, roughly speaking, that there was not enough time for any slower-than-light signal to travel from one measurement event to the other. It is one of those deliciously severe requirements that foundational physics likes to impose. Not only must you measure tiny quantum correlations, you must also arrange the geometry and timing so that relativity itself agrees the two sides could not have had an ordinary local conversation. Aspect's results again agreed with quantum mechanics and violated the Bell bound. By then it was becoming increasingly difficult to treat Bell violations as some fragile artifact of early clumsy experiments. The pattern persisted. The more carefully one tested entangled photons, the more the world refused to behave like a local hidden instruction book. And because photons are fast and polarization is cleanly measurable, the results carried a persuasive clarity that helped bring Bell's theorem from the conceptual margins closer to the centre of mainstream attention. There is something rather wonderful about the fact that light, which had already caused so much trouble for classical intuition in the history of physics, turned out to be the medium through which this particular trouble could be exposed. Light had once forced physicists to rethink waves and particles. Then it helped force them to rethink space-time. Now, in the form of entangled photons, it was helping them rethink locality itself. One begins to suspect that photons take a quiet professional pride in unsettling assumptions. At the same time, no honest telling of the story should pretend the early experiments were simple triumphal marches. They were persuasive, yes, but critics continued to point out loopholes. The detection loophole arose because not every emitted photon was actually detected. If the detected subset was somehow unrepresentative, perhaps a local hidden variable account could still mimic the observed violation. The locality loophole concerned whether the measurement settings and events were really arranged in a sufficiently independent and space-like separated way. There were also worries about how choices were generated, and whether subtle correlations in the apparatus or source might matter. This did not mean the experiments were bad. It meant the foundational stakes were so high that every possible escape hatch would be examined. And here one sees the real character of good science. The point is not to produce one dramatic experiment and declare the universe settled before lunch. The point is to improve, refine, challenge, and repeat, until the alternatives have nowhere respectable left to hide. The first great Bell experiments did not end the story. They made the rest of the story unavoidable. Once Clauser, Friedman, Aspect, and others had shown repeated Bell violations with entangled photons, the task became to close the loopholes one by one, each with still more careful experiments. Before turning toward that later phase, though, it is worth noticing the conceptual beauty of what these early experiments achieved. They took a very abstract tension between Einstein and quantum mechanics, and translated it into the language of optics tables, photon pairs, polarizers, and coincidence counters. They turned a dispute about the structure of reality into measurements of light flashing through carefully oriented devices. There is something deeply satisfying in that descent from philosophy to apparatus. It does not diminish the philosophical question, it grounds it. It says, if you want to know whether the world can be described by local hidden variables, do not just argue. Build the source, rotate the polarizers, count the clicks. The role of choice in these experiments is especially important and subtly fascinating. Bell tests are not just about particles carrying correlations. They are also about what happens when the experimenters can choose among different possible measurements. If there were only one fixed measurement on each side, hidden variables could always be arranged to match the observed correlation. The tension appears because there are several possible measurement settings, and the particles do not know in advance, at least in the locality respecting picture, which local question they will be asked. The experimenter's choices matter because they force the hidden variable model to cover multiple possibilities at once. This is why changing polarizer orientations, and later changing them rapidly and unpredictably, became so central. Choice turns passive correlation into an active test. It also gives Bell experiments a strangely conversational feel. The experimenter is not merely watching what the photons do, the experimenter is choosing how to ask, and the photons respond in ways whose joint pattern reveals what kind of world they inhabit. On each side, a question is posed by the local setting. The answer comes as a detector outcome. Only later, when the results are compared, does the deeper pattern emerge. It is as though reality has been answering in two rooms at once. And only by laying the transcripts side by side do we discover that the conversation exceeds classical limits. That image should not be pushed too far, of course, because photons do not have opinions, and if they did, they would probably be annoyingly fast about expressing them. But as a way of understanding the experimental logic, it helps. Bell tests are structured interrogations of nature. The measurement settings are the questions, the outcomes are the replies. The inequality tells us what range of overall coordination is possible if the replies were fixed by local hidden scripts. Quantum mechanics predicts a stronger coordination. The experiments showed that nature follows the stronger pattern. By the time these early great experiments had done their work, the field had changed in an irreversible way. Bell's theorem was no longer a clever argument appreciated mainly by specialists with a taste for foundational trouble. It had become part of experimental physics. Entanglement was no longer just an interpretive nuisance. It was a measurable, reproducible phenomenon with consequences for what sorts of hidden explanations remain viable. And photons, by flying faithfully through these setups and producing just the wrong kind of statistics for local realism, had helped move one of the oldest quantum debates into a new era. Still, one could not quite say the matter was finished. Persuasive is not the same as loophole-free. The experimental verdict was strong, but foundational skeptics are a resourceful species, and some of their concerns were legitimate. If one wants to say with full confidence that local hidden variables cannot explain the data, then every reasonable loophole must be shut with experimental care. That would take time, better detectors, faster switches, longer distances, more sophisticated random choice methods, and a generation of work by people determined to leave the classical escape routes as empty as possible. And that is where the path leads next, because once the first great experiments had shown the world leaning toward Bell violation, the remaining task was to make sure the universe was not winning on a technicality. Once the first Bell experiments began pointing in the quantum direction, a natural question remained, and it was not an unreasonable one. What if the universe was only appearing to violate the classical limit because the experiments were not yet perfect? Not wrong, exactly, but incomplete. Not dishonest, certainly, but vulnerable. Physics is full of cases where an early result looks dramatic and later turns out to have rested on some unnoticed bias, some hidden selection effect, some instrument that behaved beautifully right up until the moment anyone truly needed it to be trustworthy. So when Bell violations first appeared in laboratories, the next stage was not to declare the matter closed and go home feeling metaphysically refreshed. The next stage was to ask with proper stubbornness whether any local hidden variable explanation could still slip through the cracks left by the practical limitations of the apparatus. Those cracks came to be known as loopholes, and that word is well chosen. A loophole is not a proof that the quantum result is false. It is a path by which an alternative explanation might still survive. If one wishes to say that local hidden variables are truly ruled out by experiment, then one must close the loopholes carefully enough that the old local realist hope has nowhere respectable left to stand. This took decades. It required patience, technical ingenuity, and the sort of persistence that suggests experimental physicists possess a very particular relationship with disappointment, namely that they are willing to be disappointed repeatedly as long as the apparatus gets slightly better each time. The first major loophole was the detection loophole, and in some ways it was the most practical. Early Bell experiments did not detect every particle pair produced by the source. In fact, they often detected only a small fraction. Photons are quick, elusive, and not always inclined to announce their presence with the reliability one might prefer when the fate of local realism is at stake. Detectors miss events. Optical components lose photons. Sources are imperfect, and so the data used in the analysis come from a subset of all the pairs that were actually emitted. Now, this might sound like a minor inconvenience, the sort of thing one shrugs at while making a note to buy better equipment next year. But for Bell tests it mattered deeply. If only a subset of events is detected, then perhaps that subset is not representative of the whole. Perhaps the hidden variables are such that the pairs most likely to violate the Bell bound are also the ones most likely to be detected, while other pairs quietly fail to register. If that were true, then the observed sample could look more quantum than the full underlying distribution really is. A local hidden variable advocate could then say you have not disproved locality. You have merely filtered the data in a way that favours the quantum result. This concern led to what became known as the fair sampling assumption. Many early experiments effectively assumed that the detected events were a fair sample of all emitted events. That assumption was often reasonable in practical terms, and the results were still highly suggestive, but it was not ideal. If the goal is to close every loophole, one does not want to rely on assumptions that a determined critic can reject. One wants the experiment itself to leave as little interpretive breathing room as possible, so a great deal of later work focused on improving detector efficiency and source quality to the point where the detection loophole could be closed directly rather than bypassed by trust. The second major loophole was the locality loophole. Bell theorem is fundamentally about local causation, so one must be very careful that the two measurement events are arranged in such a way that no slower than light signal could travel from one to the other in time to influence the result. If the settings are chosen too early, or if the detectors are too close together, or if the relevant events overlap in the wrong way, then perhaps some ordinary local communication could still sneak in and account for the correlations. It would not have to be anything mystical. It could simply be that the experimental geometry failed to enforce the intended separation strictly enough. This is why timing and distance became so central in later Bell experiments. It was not enough merely to place two detectors in different parts of the room and feel that this seemed suitably dramatic. The arrangement had to satisfy the relativistic condition that the choice of measurement setting on one side and the measurement event on the other side was space-like separated. That phrase can sound severe, and it is severe, but in essence it means there was no time for a signal travelling at or below the speed of light to go from one event to the other. The experiment had to be designed so that if locality were to be preserved, the distant side genuinely could not know what local question was being asked. This brought in the importance of fast switching. In the earlier experiments, settings were sometimes fixed or changed too slowly. A local hidden variable theorist could then imagine that the particles left the source already correlated with the known detector orientations. To rule that out more forcefully, physicists began to change the settings while the particles were already in flight. That way, the particles could not carry detailed advance instructions tailored to a single fixed setup. The experiment itself became more like a moving target. The detectors would decide rapidly and independently how to measure each incoming particle only after the pair had already begun its journey. This was not easy. Fast random switching is conceptually elegant and technically annoying, which is exactly the sort of thing foundational physics seems to enjoy. The devices choosing the settings had to operate quickly and reliably. The timing had to be tracked precisely. The whole arrangement had to be synchronized so that one could honestly say the relevant choices and events were separated in the right space-time way. Experiments by Alain Aspect and later groups pushed strongly in this direction and made the locality loophole much harder to defend. Still, as often happens, closing one loophole entirely did not always coincide with closing another. That is one of the subtle frustrations in the history of Bell tests. For a long time, experiments could close either the locality loophole or the detection loophole, but not both at once with full confidence. Photon experiments were excellent for long-distance separation and rapid switching, so they were strong on locality. But photon detectors were inefficient, so the detection loophole lingered. Matter-based systems, such as trapped ions or other massive particles, could sometimes achieve extremely high detection efficiency, making the detection loophole much weaker, but arranging wide space-like separation and fast independent choices for those systems was more difficult. It was as though the universe had decided that every clean answer should come with a small practical obstacle course. A third concern involved the freedom of choice loophole, sometimes also called the setting independence loophole. Bell reasoning assumes that the measurement settings are chosen independently of the hidden variables carried by the particles. If that independence fails, then a local hidden variable account might still survive by exploiting a deep correlation between the state of the source and the later measurement choices. In other words, what if the universe had somehow arranged from the start that the particles and the detectors were not truly independent? then the whole Bell argument could be undercut. At first this can sound absurdly contrived, and in many forms it is. One begins to picture the cosmos engaging in prearranged conspiracies of such thoroughness that every laboratory choice has secretly been coordinated with every particle pair since the dawn of time, which is a level of administrative planning one hesitates to attribute even to nature. But as a matter of logical rigour, the point cannot simply be ignored. If the settings are not independent, Bell inequalities lose some of their force. So experimentalists sought ways of making the setting choices as independent and unpredictable as possible. Random number generators became important here, rather than letting a human calmly decide the settings in advance, or letting some predictable machine cycle through them. Experiments began using fast random processes to choose settings on the fly. Later still, some researchers used randomness derived from distant astronomical sources, including starlight and cosmic events, to push the possible common cause farther and farther back in time. The idea was not that starlight is magical, but that if a photon emitted by a star long ago is used to help set a detector orientation today, then any hidden conspiracy correlating that setting with the laboratory source would have had to begin far earlier than one might comfortably allow. It was a way of saying if you still want local realism now, you must pay for it with increasingly extravagant assumptions about the deep coordination of the universe. There was also the coincidence loophole, which concerns how one decides which events on the two sides belong to the same emitted pair. In real experiments, particles arrive at slightly uncertain times, detectors have finite response windows, and one has to establish a rule for which cliques are counted as partners. If that pairing procedure is sloppy or biased, it can distort the measured correlations. Experimental groups therefore had to refine their timing analysis and event matching procedures so that the observed Bell violation could not be dismissed as an artifact of how coincidences were selected. Then there is the memory loophole, subtler but still worth noting. Bell tests often involve many sequential trials, and one usually assumes that the outcomes of different runs do not depend on hidden memory effects, carried from one trial to the next, in a way that invalidates the statistical reasoning. If the apparatus or hidden variables somehow retained information across trials and adapted strategically, a local account might try to exploit that. This concern pushed researchers toward more careful statistical methods that did not rely too heavily on overly ideal independence assumptions. Over time, the analysis of Bell experiments became not just a matter of collecting enough counts, but of proving that the statistics themselves were robust against these more devious possibilities. What is striking in hindsight is how healthy all of this was for the science. To an outsider, it might sound as though every result was forever under siege by technical objections, but this is how a field matures. A theorem enters the laboratory. The first experiments support it. Critics identify possible escape routes. New experiments shut those routes down one at a time. Better detectors are built. Timing improves. Randomness generation improves. Statistical treatment improves. Distances grow. By the end, the result is not weaker for having faced criticism. It is stronger. Every loophole named is a loophole that can be addressed, and physics is at its best when it treats objections not as insults, but as engineering specifications. This long program eventually led to a major turning point in the middle of the second decade of the 21st century. Several groups performed what came to be called Loophole-free Bell tests, or at least experiments widely recognized as closing the two major loopholes together in a single setup. This mattered because for the first time, one could no longer say with much seriousness that the locality loophole had been closed only by leaving the detection loophole open, or vice versa. The apparatus had finally become good enough for the theorem and the experiment to lock together with unusual force. One landmark approach used entangled electron spins associated with defects in diamond, separated by a significant distance. These systems allowed very high-quality state preparation and efficient detection, while the experimental geometry and timing were arranged to preserve locality conditions. Other landmark experiments used entangled photons with dramatically improved detector efficiency, thanks in part to advances such as superconducting detectors that could catch photons with far greater reliability than older technology allowed. Fast random setting choices and space-like separation were incorporated as well. In each case, Bell inequalities were violated in a manner that left the classical local hidden variable picture with very little room to maneuver. It is important not to over-dramatize the phrase loophole-free, because in science nothing becomes absolutely metaphysically immune to every imaginable reinterpretation. One can always invent ever more radical assumptions, such as superdeterminism, where the entire experimental arrangement, including the supposed random choices, is deeply pre-correlated with the hidden variables. One can question whether the usual notions of independent choices, observer-neutral outcomes, or causal structure should be retained. Foundational debates do not disappear merely because a particularly clean set of experiments is completed. But the ordinary classical escape routes, the ones that relied on missed detections or insufficient separation, were by then largely closed. If one wanted to preserve a local hidden variable account after those experiments, the price became much steeper and much stranger. That is one of the quiet lessons of this whole history. Bell test did not merely tell physicists that the world is non-classical. Quantum mechanics had already made that plain in many ways. What Bell tests did was narrow the acceptable forms of non-classicality. They showed that the familiar strategy of saying the particles just had hidden local instructions all along cannot survive the data unless one is prepared to embrace increasingly exotic assumptions about the relation between hidden variables and measurement choices. In other words, the loopholes were not just technical nuisances. They marked exactly where the classical dream was still trying to hide. There is also a certain poetry, though perhaps a stern scientific kind of poetry, in the way each loophole forced a more careful encounter with what Bell had really assumed. The detection loophole asked whether the sample was honest. The locality loophole asked whether the distant choices were truly causally separate. The freedom of choice loophole asked whether the settings were genuinely independent. The memory loophole asked whether one could trust trial-by-trial statistics. Each one reflected a foundational principle translated into laboratory practice. If Bell theorem is philosophy disciplined into mathematics, then loophole closing experiments are mathematics disciplined into engineering. And engineering, in this story, had to become almost absurdly good. Detectors that miss too many photons are not merely inefficient, they are conceptual liabilities. A switch that changes too slowly is not merely old, it is philosophically inadequate. A random setting choice that can be anticipated is not merely predictable, it is a crack in the causal assumptions of the test. The laboratory becomes a place where metaphysics and hardware shake hands, though usually not without some tense negotiations. It is worth dwelling for a moment on the human side of this. We often speak of Bell theorem as if the universe simply handed down its verdict once the theorem was written. But in truth, the verdict had to be extracted painstakingly over decades by people aligning optics, cooling detectors, analysing timing windows, writing code, redesigning apparatus, and trying again after months of work failed for reasons too boring to appear in textbooks. There is something deeply admirable about that. The most abstract question in the foundations of quantum theory, can the world be explained by local hidden variables, ended up depending on whether actual experimental systems could be made clean enough to silence every ordinary excuse, and by and large they could. This did not mean every philosophical issue was settled in one sweep. Physicists still disagree about what Bell violations tell us most directly. Some say they reveal non-locality full stop. Others say they reveal the failure of local realism as a package, but leave room to debate which part of the package should be surrendered. Some are drawn to deterministic but non-local hidden variable theories. Others prefer many worlds, relational accounts, or information-centered interpretations. Bell experiments do not dictate a single metaphysical sermon. What they do dictate is that the easy classical sermon is over. The universe is not a place where distant entangled systems can be understood as merely carrying local, pre-existing answers independent of the measurement context in the straightforward way Einstein had hoped. By the time the loopholes were mostly shut, Bell's theorem had passed from provocative idea to established guidepost. Local hidden variable explanations were no longer attractive because quantum theory sounded dramatic. They were untenable because repeated, increasingly careful experiments had denied them shelter, and that means the remaining question becomes even more interesting. If Bell's theorem has ruled out the old local hidden picture, then what exactly is it telling us about the structure of the world? Are two things really affecting each other instantly? Is the universe fundamentally non-local? Is reality less about separate objects and more about holistic states and relations? Or is the true lesson even stranger, namely that our classical way of asking what exists where may need to be revised from the ground up? Those questions do not disappear once the loopholes close. In a way, they only become unavoidable. By the time one has followed Bell theorem through the experiments and watched the loopholes close one by one, the obvious next question is not whether something important has happened. It plainly has. The harder question is what exactly the result is saying about the world. That is where the story becomes both more exciting and less tidy, because Bell theorem gives a very strong negative answer and a more open-ended positive challenge. It tells us with unusual force what the universe is not like in one classical sense. It tells us less directly how to describe what the universe is like instead, and perhaps that is why it remains so compelling. The theorem closes a door with great confidence, but the room beyond that door can still be furnished in more than one way. The first thing Bell theorem says is that the old classical picture of distant systems, carrying fully local pre-existing answers, cannot be the whole truth. That is the simplest honest summary. If two entangled particles are measured far apart, the correlations they display exceed what any straightforward local hidden variable theory can produce. So the universe is not built in quite the way Einstein hoped when he imagined that each particle might simply carry its own local reality with it, independent of any distant measurement choice, and that the strange quantum predictions would eventually be explained by a deeper but still local theory beneath the surface. Bell showed that such a theory would leave a statistical fingerprint. The experiments do not show that fingerprint. They show something else. This means the world is not merely classical underneath a blurry quantum surface. The blur is not just ignorance in the ordinary familiar sense. The quantum correlations are too strong for that. If one wants to keep a hidden variable view at all, then one must give up strict locality in the Bell sense, as happens in Bohmian mechanics, or else revise some other assumption so radically that the classical dream no longer looks classical anyway. The easy comforting idea that particles separate, carry definite local properties, and later reveal them under measurement without any deeper conceptual cost has not survived. That is already a very large claim about the universe. At the same time, Bell theorem does not tell us that signals can be sent faster than light. This point is so important that it deserves repetition even at the risk of sounding slightly parental about it. The theorem does not give us instant messaging through entanglement. It does not let one observer choose an outcome on one side and thereby force a chosen outcome on the other side in a controllable way. Each local measurement result still appears random when viewed on its own. It is only when the data from both sides are later compared that the extraordinary pattern emerges. So whatever Bell theorem says about the universe, it does not overthrow relativity in the ordinary practical sense of allowing usable superluminal communication. The world remains strange, but it also remains stubbornly unwilling to become convenient. This creates an important distinction between signalling and correlation. In ordinary life, when we think of one thing affecting another, we often imagine control. If I push a door, the door opens. If I press a switch, the light comes on. There is a clear local relation between my action and the effect. Bell theorem points to something subtler. The entangled systems display a pattern of coordination that no local hidden script can explain, yet neither side can use that coordination to control the distant outcome directly. The relation is real, but it does not behave like an ordinary classical cause that you can harness at will. This is one reason the result feels so conceptually slippery. It tells us the universe contains a form of connectedness stronger than local classical realism allows, while still refusing to hand us the kind of overt instant influence we instinctively know how to picture. So what does that imply? One possible lesson is that nature is non-local in a deep sense. Many physicists are comfortable saying exactly that, provided one is careful about what non-local means. It does not mean hidden messages shooting through space in blatant violation of relativity. It means that the structure of physical reality cannot be fully decomposed into separate local pieces carrying complete independent facts. There are holistic features of entangled systems that belong to the pair as a whole, and cannot be reduced to local states plus shared classical history. In that sense, reality is less separable than classical physics led us to expect. The distant parts of the world are not always as independent as they look. That idea of separability is worth lingering over because it may be closer to the heart of the matter than the dramatic language of instant action. Classical physics trains us to think that if two systems are far apart, then the complete state of the whole should just be the complete state of one plus the complete state of the other, together with any ordinary causal connections they have had. Bell theorem, together with entanglement, tells us that this decomposition fails in an important way. The state of the whole can contain more structure than the sum of local facts. The pair is not just two separate things with a shared past. It is one non-classical arrangement whose measurable relations outrun local description. That is not merely a curiosity about particles. It is a statement about the architecture of the world. Now, different interpretations of quantum theory take this lesson in different directions. This is where Bell theorem stops being a neat universal slogan and starts becoming a crossroads. If you're drawn to Bohmian mechanics, then Bell theorem says the underlying theory must be non-local. Bohmian mechanics accepts that price openly. It gives particles definite positions and a deterministic evolution, but the guiding structure that governs them depends on the whole arrangement in a way that is not locally separable. So in that interpretation, the theorem says the universe is real, definite, and non-local. One recovers many of the features Einstein wanted, but not locality. If you are drawn to many worlds, the lesson can sound different. In that picture, the wave function evolves smoothly and universally without collapse, and measurement outcomes branch into different observer histories. Bell correlations arise from the structure of the universal state, rather than from local hidden variables or instant signaling. On that view, Bell theorem does not force mysterious faster-than-light influence. Instead, it tells us that the classical idea of a single pre-existing outcome carried locally was too narrow. The universe is larger and more branching than common sense imagined. Whether one finds it reassuring or alarming may depend on how one feels about there being countless versions of oneself not tidying the kitchen. If one favours relational or information-centred interpretations, the emphasis shifts again. Then Bell theorem may be taken to show that physical facts are not all absolute, observer-independent local items waiting passively to be read off the world. Instead, the significance of outcomes and states may depend on relations between systems, on the information available in a given context, or on the operational structure of measurement itself. In that style of thinking, the theorem does not simply shout non-locality. It challenges the classical ideal of a complete observer, neutral inventory of local properties existing in the background. It says that the way reality presents definite facts may be more contextual and less classically object-like than older pictures assumed. Still others take Bell theorem as evidence that one must rethink causation itself. We are used to a world in which causes spread continuously through space and time. Bell violations suggest that the quantum world does not fit comfortably into that picture if one insists on keeping local hidden variables. Some philosophers and physicists therefore explore whether causation in the quantum domain is not the most fundamental category, or whether the causal network we infer at the macroscopic level emerges from something deeper that is not organised in fully classical local terms. That is an unsettling thought, but Bell theorem gives it serious motivation. It is not fantasy for its own sake, it is a response to a precise experimental tension. There is also a quieter but profound lesson about realism. Bell theorem does not necessarily force us to abandon realism entirely, because some realist interpretations survive by giving up locality or by reworking what counts as a real state. But it does tell us that realism cannot be the simple classical kind, in which every possible measurement outcome is already encoded as a local fact waiting to be uncovered. The universe does not appear to contain that sort of full local answer sheet. If properties are real, they are real in a way that is more structurally entangled with measurement context, with the global state, or with non-local relations than classical intuition expected. This is why Bell theorem has such a peculiar emotional effect. It does not merely tell us that the world is odd in some isolated technical corner. It reaches right into the assumptions that make the world feel intelligible. We like to think that distant things are separate, that properties are local, that measurement reveals rather than helps define, and that common causes in the past can explain any strong coordination in the present. Bell theorem says that package is too optimistic. Some of its pieces can perhaps be saved, but not all at once, and not in the familiar form. Another way to put this is that Bell theorem teaches humility about the relationship between appearance and structure. At the scale of daily life, the world looks local and separable. Tables sit where they are. Cats occupy chairs with a confidence wholly disproportionate to their legal ownership of the furniture. Signals take time, causes spread. All of that remains true enough for practical living. But Bell theorem suggests that beneath this macroscopic order lies a quantum structure in which the world is not simply built from self-contained local facts. The classical picture works wonderfully as an approximation or emergent description, but it is not the final blueprint. At the deepest level we have tested, the universe keeps more of itself knit together than common sense would guess. This has consequences beyond philosophy. It changes how we think about information itself. Entanglement, once treated as an interpretive nuisance, became a practical resource, precisely because Bell-type correlations reveal that quantum information is not just classical ignorance in disguise. A pair of entangled systems contains a relational structure that can be used in cryptography, teleportation, and quantum computation in ways no classical local hidden account can fully mimic. Bell theorem helped clarify that this is not a clever illusion. The resource is genuinely non-classical. The universe is offering something more than sophisticated bookkeeping. It is offering a different pattern of possibilities. There is also something deeply revealing here about the way science advances. Bell theorem does not give us a photograph of ultimate reality. It gives us a constraint on acceptable stories. That is often how foundational science works. It narrows the space of intelligible description. It tells us which pictures cannot survive contact with experiment. In this case, the theorem says any story that tries to explain entangled correlations by means of local pre-existing hidden instructions is ruled out. That does not uniquely identify the winning interpretation, but it does clear away a whole region of conceptual comfort, and sometimes that is more valuable than a premature false clarity. One must also mention the possibility of more radical responses, because Bell theorem has driven some people to them. Superdeterminism, for instance, attempts to preserve locality by denying that measurement settings are genuinely independent of the hidden variables. In that picture, the entire experimental arrangement, including the choices of settings, is deeply correlated from the start. Bell inequalities are then sidestepped because one of their key assumptions fails. But this comes at an enormous conceptual cost. The universe begins to look less like a lawful arena and more like a perfectly choreographed conspiracy in which every apparently free or random choice was built into the conditions from the beginning. Some people explore this seriously. Others regard it as a cure worse than the disease. Either way, the fact that one must go to such lengths says something about how hard Bell theorem presses on the classical local picture. There is a related lesson about freedom and independence in experiments. Bell theorem depends on the idea that the settings can be chosen independently of the particle's hidden states. The more carefully experiments ensure this, the more impressive the violation becomes. So the theorem is not only about particles and detectors, it is also about the autonomy of questions. The universe seems to care that we can ask different local questions without those questions having been secretly coordinated with the particles in a classical local way. That is an unusual feature for a theorem about the foundations of physics. It links the structure of reality to the structure of inquiry itself, and then there is the question that never quite goes away. Do two things affect each other instantly? Bell theorem does not answer that in a simple yes or no. If by affect each other instantly one means ordinary controllable signalling or causal pushing, then no, not in the sense the theorem itself establishes. If by it one means that the outcomes of distant measurements are tied together in a way no local hidden story can explain, then yes, there is clearly a non-classical connectedness that survives separation. The difficulty is that our everyday word effect carries too much baggage from macroscopic causation. Bell theorem reveals something more subtle than a push, and more structured than a coincidence. The entangled systems are not independent in the old classical sense, but the connection between them does not behave like a usable instant force. The theorem leaves us in a middle ground that is more exacting than poetry, and less familiar than common sense. This is why some physicists prefer to speak of non-local correlations rather than non-local causes. The phrase sounds drier, but it avoids suggesting too much. Correlations are what the experiments directly display. Whether those correlations should be read as evidence of non-local influence, holistic structure, branching worlds, relational facts, or some other underlying ontology depends on the broader interpretive framework. Bell theorem tells us the correlations cannot come from local hidden variables. It does not settle all the metaphysical housekeeping beyond that. But even this more cautious phrasing already says something extraordinary about the universe. It says that distance does not restore classical independence to entangled systems, even when no signal can pass between them in the relevant time. There is perhaps an even deeper moral. Bell theorem reminds us that reality is not obliged to satisfy every principle we would like to preserve simultaneously. Physicists once hoped to keep locality, realism, determinism, separability, and the quantum predictions all together. Bell showed that this is too much to ask. The universe declines the full package. That does not mean science has failed. Quite the opposite. It means science has reached a level of precision at which even our most cherished conceptual combinations can be tested and, when necessary, refused. There is something bracing about that. The world is not arranged for our comfort. It is arranged however it is, and Bell theorem is one of the clearest examples of nature telling us to revise the terms of our understanding. Even so, one should not leave the matter sounding grim. There is wonder here, as well as disruption. A universe in which entanglement exists, in which distant systems share correlations no local classical account can match, is not merely a universe that has denied us simplicity. It is also a universe richer in structure than earlier physics imagined. The world is capable of forms of relation that classical thought never anticipated. It contains patterns that are not reducible to little local parcels of pre-existing fact. That is a loss for one style of common sense, certainly, but it is also a gain in depth. The universe has turned out to be more subtle than its daylight appearance suggests, and perhaps that is why Bell theorem continues to feel less like a completed lesson than an opening. We know now that the local hidden variable dream does not fit the evidence. We know that entanglement forces a rethinking of separability, and perhaps of causation itself. We know that quantum theory is not just probabilistic bookkeeping over a classical hidden base, but the positive picture of what the universe most fundamentally is remains contested. Bell theorem does not end the conversation, it sharpens it. It tells us what kinds of worlds are no longer available, and by doing so it leaves us standing before a smaller but stranger set of possibilities. That smaller set includes worlds that are non-local in a disciplined sense, worlds that branch, worlds where facts are more relational than absolute, worlds where hidden variables survive only by abandoning Einstein locality, and worlds in which our most classical intuitions about what exists where must be treated as emergent rather than fundamental. None of those pictures feels as immediately comfortable as the older one in which distance simply keeps things apart. But Bell theorem has taught us not to confuse comfort with truth. The world is under no obligation to look classical when examined carefully enough. So what Bell theorem says about the universe is not one sentence, but a family of hard-won lessons. It says the deep structure of reality is not captured by local pre-existing classical facts. It says entangled systems carry a kind of connection that cannot be reduced to shared hidden scripts. It says the old dream of locality plus hidden definiteness has failed experimental judgment. It says that information, relation, and structure matter in a more global way than classical physics expected. And it says that even when the world refuses faster than light signalling, it may still refuse classical separability too. That is a difficult message, but it is also an oddly beautiful one. The universe, when questioned with enough care, has answered that distance is not always the final word on relatedness. Separate places are real, and signals still take time, and relativity still governs the traffic of usable causes. But somewhere beneath that orderly surface, entanglement has shown that the world is woven more tightly than it first appears. And that leaves one final mood to inhabit, not the need to force a single neat conclusion, but the quieter recognition that even after all these experiments and all this reasoning, some part of the mystery remains standing, patient as ever, just ahead of where our language feels entirely at home. And so we arrive at the point in the journey where the question becomes quieter, not because it has been fully answered, but because we have followed it as far as honesty will comfortably allow, before the remaining mystery begins to look back at us. We started with a simple-sounding thought: can two things affect each other instantly? Along the way, that thought opened into Bell theorem, entanglement, hidden variables, locality, experiments with photons, and the strange realization that the universe does not seem especially interested in preserving all the habits of thought that classical physics taught us to trust. Distance still matters. Signals still take time. Relativity still keeps its stern and beautifully organized watch over the traffic of causes. And yet entangled systems remain connected in a way that no local hidden script can fully explain. Near and far, it turns out, are not the whole story. There is something deeply human about how unsettling that feels. We are creatures who rely on separation. We divide the world into here and there, before and after, mine and yours, this room and the one beyond it. We build our practical lives on the assumption that distance creates independence. If something happens in the next town, it may matter to me eventually, but not before something carries the news. If someone lights a lamp on a distant hill, the glow must travel. If a friend chooses tea instead of coffee several streets away, my own breakfast remains mercifully unaffected. The world seems orderly because space behaves like a patient organizer, keeping things in their places and forcing causes to mind the route between them. Bell theorem did not destroy that practical order. It did not cause clocks to run backward, or letters to arrive before they are sent, or spoons to begin taking spontaneous interest in remote events. Your furniture remains admirably committed to local realism for all the purposes that matter to a tired person on an ordinary evening. But Bell theorem did reveal that the deeper structure beneath this calm appearance is not as separable as it looks. When quantum systems are entangled, their relations cannot be understood as merely the result of shared hidden instructions carried outward into independent local futures. Something more is present. Not a useful, faster-than-light signal, not a tidy, invisible wire stretching between particles, but a pattern of connection that classical local thinking cannot fully contain. That is perhaps the most unsettling and also the most beautiful part. The universe has not replaced one easy story with another. It has simply told us that the first easy story is not enough. Distance remains real, but not absolute in the way we imagined. Locality remains powerful, but not complete as a classical explanatory ideal. The parts of the world can no longer always be understood as tiny private kingdoms, each carrying a full and independent account of itself. Sometimes the whole contains more than the sum of local pieces. Sometimes what is true of the pair cannot be fully reduced to what was already true of each member alone. That is a difficult thing to picture, but then the universe has never shown much concern for whether our preferred pictures are easy to draw, and perhaps that is why Bell theorem feels so different from many other scientific results. It is not only telling us something about particles or light or laboratory devices, it is telling us something about what it means for reality to be stitched together at all. For centuries, the great dream of physics was that one could understand the world by breaking it into smaller and smaller units, each with its own local properties, each behaving according to local rules, each handing causes forward in orderly sequence. That dream was fruitful beyond measure. It gave us mechanics, electromagnetism, thermodynamics, relativity, and much of the technological world that now surrounds us humming softly in the background. But Bell theorem suggests that when we reach the quantum level, the dream requires revision. The world is not made only of isolated local facts waiting to be catalogued, like items in a very ambitious cupboard. This does not mean reductionism is worthless or that analysis has failed. Far from it. Bell theorem itself is a triumph of analysis. It is what happens when one takes a philosophical hope, examines its logical consequences, and asks the laboratory to decide. But the result says that whatever the deepest pieces of the world are, they do not combine according to the old purely classical recipe. They admit relations that are not just ordinary leftovers from a common past. They participate in a structure that remains global in a way that classical common sense finds impolite. There is also a more personal lesson in this, though not in the sentimental sense. The sciences are often said to remove comfort from the world by replacing old warm images with colder and more exacting ones. Sometimes that is true. It is difficult to hear that the Earth is not central, that time is not universal, that much of the cosmos is made of things we do not directly see, and that particles do not politely carry complete local answers wherever they go, without feeling that reality has become a little less domesticated. But there is another side. Bell theorem does not merely subtract, it reveals richness. It says the universe contains forms of relation that classical thought never anticipated. It says the architecture of the world is more subtle, more interwoven, and in a certain sober scientific sense more intimate than it first appears. That intimacy is not the kind found in poetry, though poetry has certainly tried to borrow it. It is not evidence that minds are magically connected across continents, or that the cosmos is secretly arranging our personal lives with quantum tenderness. Bell theorem offers no support for mystical overreach, no matter how attractively packaged. It is about specific physical systems and precise correlations, yet even within that discipline, one can feel the philosophical force of the result. The universe is not built from little islands as neatly as we once thought. There are structures in nature that remain meaningful across separation. There are states that belong to wholes more than to parts. And there are questions whose answers remind us that understanding does not always mean recovering what common sense would have guessed in advance. If that sounds abstract, it may help to return to what the experiments actually accomplished. Physicists created entangled systems, separated them, chose how to measure them, and found again and again that the resulting correlations violate the limits any local hidden variable theory would respect. These were not vague impressions. They were detector clicks and timing windows and carefully randomized settings and long nights in laboratories where the coffee probably varied in quality but the patients did not. The mystery remained, but it remained after serious questioning, after skepticism, after loopholes were named and closed and named again. It is one thing to say the world is mysterious because we have not looked closely enough. It is another to say the world remains mysterious after we have looked with extraordinary care. Bell theorem belongs to the second category, and that matters. It means the unresolved part of this story is not a temporary embarrassment waiting for a routine patch. It is not like misplacing one page of a manual, and hoping the rest will make sense once the drawer is cleaned. The unresolved part is structural. Even after Bell, even after the great experiments, even after loophole-free tests, physicists still disagree on what exactly the theorem tells us to give up. Some are willing to surrender locality in a deep sense and keep realism. Some are willing to revise realism itself. Some accept branching worlds. Some prefer relational views. Some flirt with extremely radical ideas about determinism and the independence of measurement choices. The theorem narrows the possibilities, but it does not reduce them to one cheerful sentence everyone can print on a mug. This is not a weakness. It is, in a way, the mark of a profound result. Important theorems do not always hand us a final picture. Sometimes they perform a stricter and more valuable task. They tell us which pictures are no longer available. Bell theorem closed one of the most cherished escape routes from quantum strangeness. It told physics that the world cannot be explained as a network of local pre-written instructions hiding underneath the quantum formalism. That negative result is so strong that everything else now unfolds in its shadow. Any interpretation worth taking seriously must pass through Bell. Any account of reality that hopes to preserve the old separable classical order must now pay a price so steep that it begins to look like a different philosophy altogether. And yet, despite all this, the ordinary world remains ordinary enough to live in. This is one of the most curious features of deep physics. The foundations may be astonishingly strange while the visible surface of life stays comfortingly stable. You still put the kettle on and wait. You still misjudge how long a cue will take. You still lose track of time while reading something interesting and become acutely aware of it, while waiting for an email that should have arrived already. None of this requires Bell theorem. The moon does not need an interpretive preference to rise. Your shoes do not become less local because entangled photons violate an inequality. The macroscopic world remains practical, navigable, and almost suspiciously uninterested in the philosophical panic occurring beneath it. Perhaps that is part of what makes these ideas so soothing as well as unsettling. There is a strange calm in knowing that the universe can be far more subtle than our instincts, while still allowing us to live among tables and teacups and familiar roads. Reality does not owe us classical simplicity, but it does grant us stable approximations. That is no small kindness. We are able to survive and think because the world, though deep down non-classical, presents itself at our scale in patterns we can learn and trust. Bell theorem reminds us that those patterns are not the whole truth, but it does not strip them of usefulness. The map of daily life still works, it is just not the final map. There is also something humbling in the way Bell theorem links the very small to the very philosophical. 2 photons in a laboratory, 2 settings chosen by fast switches, 2 detectors separated by enough space and timed with enough care, and suddenly one is no longer talking only about optics. One is talking about the limits of locality, about the nature of reality, about whether the world can be understood as a collection of independent local facts at all. It is a reminder that the foundations of existence are not always hidden in enormous dramatic places. Sometimes they arrive in the quiet discipline of a table full of equipment, in the patient accumulation of data, in the refusal of a statistical pattern to fit the old story. And even here, one should resist the temptation to pretend that physics has become mystical. Bell theorem did not reveal magic. It revealed constraints. It revealed that nature obeys quantum correlations and refuses certain classes of classical explanation. That may sound less romantic, but in many ways it is more impressive. Magic is merely the refusal to explain. Bell theorem is explanation pushed until it collides with the edge of classical assumption. The mystery that remains is not a blank wall. It is a shaped mystery, a disciplined one, a mystery with boundaries drawn by theorem and experiment. We know more clearly than before what cannot be true. That is an achievement worth savouring. I think there is also a reason this subject lingers in the imagination beyond professional physics. It touches a very old tension in human thought, the tension between separateness and connection. We experience ourselves as individuals, each living from one particular vantage point, each moving through local space, each bound by the limits of our own bodies and histories. And yet we're also endlessly drawn to the thought that things may be linked more deeply than they seem. Most versions of that thought drift quickly into sentiment or superstition. Bell theorem does something rarer. It gives us a rigorously tested example of connection that is real without being mystical, precise without being easily pictured, and powerful without becoming controllable in the ordinary sense. It says the world contains relation more subtle than common sense allows, and it says so with laboratory evidence rather than wistful hope. That does not solve the emotional problem of what to do with such knowledge, of course. The universe is under no obligation to become easier to imagine simply because we have measured it. But perhaps imagination is not the final standard. Physics has often asked us to accept realities that outrun direct visualization. Earth circles the sun though the ground feels still. Time dilates, though clocks in our hands seem steady. Matter is mostly empty space, though the table feels solid. Bell theorem belongs in that same family. The world is less locally classical than it appears, even if our minds still reach instinctively for local pictures. The challenge is not to force the universe back into the old image, but to let our understanding grow more careful around the new one. In that spirit, it may be helpful to notice that the mystery remaining after Bell is not a failure to decide whether the universe is orderly. It is a question of what kind of order it has. The classical ideal was one kind of order: local, separable, deterministic, picture-friendly. Quantum theory, together with Bell, points toward another kind: statistical but exact, relational in deep ways, structured without always offering local pre-existing answers. The order is still there. In some respects it is stricter than ever. Bell inequalities are not loose impressions. Quantum predictions are not vague moods. The difficulty is not that the world lacks order. The difficulty is that the order no longer flatters our older habits of imagination. And so we return, gently, to the opening thought. Can two things affect each other instantly? After all this, the best answer is not a slogan but a careful pause. If what you mean is, can one observer send a deliberate faster-than-light message by manipulating one half of an entangled pair, then no. If what you mean is, are distant entangled systems linked in a way that no local hidden variable account can explain, then yes, unmistakably so. If what you mean is, does the universe contain a form of connectedness more subtle than ordinary local causation, then Bell theorem strongly suggests that it does. The difficulty is that our everyday word effect is too blunt for the job. The connection is real, but it is not a simple push. It is not the old machinery of cause dressed in a more glamorous suit. It is its own kind of relation, and we are still learning the most faithful language for it. That unfinished language may be the truest sign that the mystery remains. Science is at its best not when it pretends to have completed every sentence, but when it knows exactly where its knowledge becomes delicate. Bell theorem marks one of those places. We know enough to reject the easy local hidden story. We know enough to engineer entanglement and use it in technologies of astonishing subtlety. We know enough to say that reality is more globally structured than classical common sense suspected. And still, we do not all agree on the final ontology, on the most honest metaphysical picture behind the successful mathematics. That is not failure. That is the frontier wearing a very precise expression. So wherever you are listening from tonight, perhaps now a little later than when we began, I find there is something quietly comforting in that. The universe is not fully pinned down, not conceptually domesticated, not exhausted by the brightest theories we have. There are still edges where knowledge opens into wonder without dissolving into nonsense. There are still questions that remain serious even after decades of theorem and experiment, and there is still room, even in the hard, polished machinery of the modern physics, for a kind of humility that feels almost old-fashioned. We can measure with extraordinary precision and still admit that the final picture is not yet settled. If you have stayed with me through photons and hidden variables and the stern little miracles of Bell inequalities, thank you. I hope this quiet excursion into one of physics' most beautiful difficulties has given you something to think about, or perhaps just something calm and strange to drift alongside while the day recedes. And I would love to know, just as at the beginning, where in the world you're listening from, and what time it is in your corner of things right now. It feels fitting somehow. We have spent this long, gentle stretch talking about distance and connection, about here and there, about near and far, while listeners scattered across the globe arrive together at the same final hush. If you found this soothing, or intriguing, or simply a pleasant way to let the mind loosen its grip on the day, a like and a subscription would be very warmly appreciated. It helps this little space of calm science find other listeners who may want a slower path into sleep or into wonder, or perhaps into both at once. And if the subject has left you more awake than before, well, there are worse reasons to be awake than having spent an hour in the company of one of the strangest truths modern physics has uncovered. For now, though, I think it is enough to leave the matter there, not tied up too tightly, not forced into certainty it has not earned, but resting where good questions often rest, between understanding and awe. The world nearby remains solid enough to hold you. The world far away remains bound by light and distance, and somewhere beneath both, quiet as ever, reality keeps more of itself connected than it first lets on. Sleep well, wherever you are, and however far your own thoughts may have travelled tonight.